Hello there, and welcome to The Tired Thinker, a quiet little corner where ideas drift, twist, and sometimes circle back on themselves. Tonight's slow journey is about something mysterious, unsettling, and strangely beautiful. Time loops. Moments that repeat, days that restart, histories that never quite escape themselves. From ancient myths to modern physics, there are theories that suggest time might not be a straight line at all, but a circle or even a knot. We might never notice these loops, yet they could shape everything. Your memories, the rise and fall of civilizations, even the flow of the universe itself. Before we step into these repeating mysteries, I'd love to know, where are you listening from? And what time is it right now, in your little corner of this ever-turning timeline? It's strange, isn't it? A video about loops, and here we are, scattered across space and time, connected for this one shared moment. If you find this kind of slow, thoughtful wandering comforting, or if you're just here to rest your mind after a long, tangled day, it would mean so much if you gently liked the video or subscribed. It helps this small channel find others who might need a soft moment to wonder too. Now, let's step into the loop together. Imagine you're walking across a street. Suddenly, a car runs a red light and speeds toward you. You freeze. In one world, the car hits you and everything goes black. In another, the car misses you by inches and you make it to the sidewalk, shaken but alive. Quantum immortality begins with this kind of situation, life or death, where the outcome could go either way. Quantum immortality comes from a thought experiment based on quantum mechanics. It starts with the idea called the many worlds interpretation. This interpretation says that every time something can happen in more than one way, all the outcomes actually do happen in separate branching worlds. You see one outcome, but the others still exist, just in different versions of reality. Let's go back to the street. In the world you know, you were either hit or not. But if the many worlds idea is correct, there's a version of you who always survives the accident, no matter how unlikely. Quantum immortality takes this further. It suggests that, from your point of view, you can never experience your own death. Even if there's a tiny chance you live, you will always find yourself in the world where that chance came true. That doesn't mean you can't die. People around you will see your death, but in your own awareness, you keep going. You only ever feel like you survived. In another case, say you fall from a tall building. In most worlds, you hit the ground and die. But in one world, a gust of wind pushes you just enough that you land in a dumpster and survive. The odds are almost zero, but not quite. That's enough. This idea depends on two key parts. First, that consciousness sticks to one line of events, your timeline, your thread through the multiverse. Second, that there is always some non-zero chance of survival, no matter how small. If both of these things hold true, then, from your point of view, you never stop being aware. You skip past all the versions of you that die and follow the rare line where you live. You might ask what happens when you get old. Bodies wear out, hearts stop beating, brains break down. Can quantum immortality still apply? The theory says yes, though it gets stranger. In each branching world, something different happens. Maybe in one, medicine advances just in time. In another, a rare mutation protects you from disease. The version of you that keeps going always experiences the reality where life somehow continues. But there's a catch. These survival paths don't make life better. You may survive events that should have killed you, but you might be badly hurt or stuck in pain. You might live in worlds where everything else is worse, where others died, or where the environment collapsed, or where you are alone. In this view, immortality isn't peace, it's endurance. Some thinkers use a thought experiment called the quantum suicide machine to explain this further. It's not real, but it helps clarify the point. Imagine a device that measures the spin of a single particle. If the result is one value, the machine fires a gun. If it's the other, the gun clicks empty. In each trial, two worlds form, one where you die, one where you don't. The person running the test only ever feels the outcomes where they survive, even if by chance. To everyone else, they are dead. To themselves, they never die. This shows how quantum immortality is a private experience. It's not something others can confirm. It also relies on the assumption that your mind can move across these branches, always tracking the path where you're still alive. That part is hard to prove, and many physicists doubt it works that way. The many worlds interpretation itself is still a theory. No one has found a way to test it fully, and consciousness remains poorly understood. Still, the concept raises deep questions. What does it mean to survive? Is awareness enough? Suppose you live but suffer brain damage. In some branches, you might remain alive but unaware. Does that count? Quantum immortality doesn't promise a good life, just a continued one. Imagine someone with a terminal illness. In most branches, the disease ends their life. In one rare branch, a new treatment works. In another, their body reacts in an unusual way and heals. These outcomes are unlikely, but if the many worlds view holds, then they happen. That person, from their point of view, would find themselves in the branch where they keep living. Even if everyone else saw them die, their awareness would carry on in the rare cases where it didn't. Another case could be a soldier on a battlefield. Bullets fly, explosions shake the ground. Most versions of the soldier don't make it home, but in one timeline, a shell lands nearby and doesn't go off. In another, a bullet misses by a hair. The soldier survives in some thin thread of possibility, and from their own point of view, that's the only thread they ever follow. This leads to a strange view of life. If quantum immortality is real, you may never feel your own end. You may pass through worlds of growing odds, surviving again and again, while everything around you falls away. Over time, the world may look more broken as fewer things go right. The longer you live, the rarer your survival, and the more twisted the reality that still allows it. The idea is not new. People have dreamed of immortality for centuries, but quantum immortality offers a version that doesn't rely on magic or machines. It depends only on physics and on the idea that if something is possible, it happens somewhere. Still, even if the theory is true, it doesn't mean you should act like you can't die. To everyone else, you can. You do. Quantum immortality, if it exists, is something only you experience, and you won't know it's happening. You will just feel lucky again and again, while the rest of the world carries on without you. So when you think about this idea, it's not about hoping for eternal life. It's about understanding the strange edge of what science allows, and what it might mean to be aware in a world that never stops splitting. Imagine looking into a mirror. You see yourself, but something feels different. Your image moves when you move, but it flips everything left to right. Now, imagine a whole universe like that, flipped in a way we can't see, made of particles that behave in reverse, following different rules. This is the idea behind the mirror universe hypothesis. The mirror universe hypothesis suggests that another universe exists alongside ours. It contains mirror versions of everything we know: mirror particles, mirror atoms, mirror stars, and maybe even mirror life. These things wouldn't be visible to us. They wouldn't reflect light in the way we expect. They wouldn't interact with our particles using normal forces, like electromagnetism. That makes the mirror universe almost invisible to us, even if it exists right next to ours. Physicists first explored this idea while studying parity. Parity means symmetry in space. If a process happens one way and you flip it like a mirror image, parity says it should still work the same. For a long time, Scientists thought the laws of nature always obeyed parity. Then, in 1956, two physicists, Tsung-Dao Lee and Chen-Ning Yang, suggested testing whether that was true for weak nuclear forces. Soon after, experiments showed that weak interactions do not respect parity. They behave differently in a mirrored setup. This discovery raised a question. If the weak force breaks parity, could nature restore balance by hiding a mirror version of it somewhere else? What if there is a full set of mirror particles that follow the same rules, but in a mirrored way? These mirror particles wouldn't interact with us through the usual forces, so they would be hard to detect. In this mirror world, mirror matter would behave like normal matter. It would form mirror atoms, mirror molecules, and mirror structures like planets and galaxies. But because mirror matter wouldn't use our light, we wouldn't see it with telescopes. It might explain dark matter, stuff we know is out there because of its gravity, but that we can't see or touch. Suppose you drop a ball. It falls to the ground. That's gravity. Now imagine you're in a universe made of mirror matter. You drop a mirror ball, and it also falls, pulled by mirror gravity. If the two universes only connect through gravity, then their effects could reach across. A large mirror galaxy could bend space in our universe. We would see stars behaving oddly, speeding up or curving around something invisible. That's how scientists describe dark matter. Mirror matter might be the reason galaxies hold together when they should fly apart. Think of a room filled with regular air. Now imagine another room next to it, filled with nearer air. The two rooms are in the same building, but separated by a wall. You can't breathe the mirror air. You can't feel it, but its weight presses on the wall. That pressure, though faint, still has effects. In the same way, the mirror universe could press on ours with gravity. Some versions of the hypothesis suggest that mirror particles have tiny ways to mix with normal particles. For example, a photon, the particle of light, might mix slightly with a mirror photon. If this happens, then under rare conditions, particles could switch between the two sectors. That might show up in experiments as particles disappearing or reappearing. Scientists have tried looking for this, but so far, results are unclear. One experiment involves neutrons. Neutrons are neutral particles found in atoms. Researchers placed neutrons in a chamber and waited to see how long they lasted. In some tests, the neutrons disappeared faster than expected. One idea is that they could be switching into mirror neutrons, escaping into the mirror world. This isn't confirmed, but it keeps interest in the hypothesis alive. In theory, a mirror universe could have its own version of chemistry, biology, and even intelligence. If mirror life exists, it would be made of mirror atoms. Its thoughts, actions, and senses would use mirror signals. It wouldn't know about us, just as we wouldn't know about it. Or maybe it would, if small connections between the worlds let signals pass now and then. Let's say a mirror civilization evolved in a mirror galaxy. It sends out mirror signals across mirror space. Those signals wouldn't reach us the way radio waves do. They wouldn't push our electrons or warm our detectors. But if the two universes share gravity, those signals could still leave slight marks, tiny ripples in space or shifts in cosmic patterns. We don't know how to see those yet, but we keep searching. Some scientists use the mirror universe hypothesis to try to fix problems in physics. One issue is symmetry. Many equations look more balanced if mirror particles are included. Another is the matter-antimatter imbalance. At the Big Bang, matter and antimatter should have been made in equal amounts. But we see far more matter today. Mirror matter might balance that scale without showing up in the usual ways. Others look at the early universe. It was hot, dense, and fast expanding. If a mirror sector existed from the start, it would evolve in its own way. Its light would stretch and cool, just like ours. Maybe we can spot signs of it in the cosmic microwave background, a faint glow left over from the Big Bang. Small irregularities in that glow might carry hidden hints. The mirror universe idea is not the same as the multiverse. In the multiverse, other universes have different laws of physics. In the mirror universe, the laws are the same but reflected. Think of it more like a hidden twin, not a distant cousin. You could imagine two people walking side by side, one in the regular world and one in the mirror world. They live parallel lives but never meet. Their choices, their histories, their physics all match, that flipped. They move in sync, though unaware of each other. Every step leaves a mark, even if it's not visible, even if we never find direct proof. The idea of a mirror universe gives us a useful lens. It lets us ask, what if the world has more layers than we can see? What if what we call missing is not missing, just hidden, moving through the same space, but along a different thread? Thinking this way doesn't change what we know, but it widens the scope of what we can imagine. Imagine you walk into a room and see a chair. You touch it, you feel its shape, you hear your footsteps on the floor. It seems obvious that the chair and the room exist, even if no one else is there. But for George Berkeley, an Irish philosopher from the 1700s, this idea is mistaken. He argued that things do not exist outside of perception. In simple terms, he believed that to be is to be perceived. This view is called idealism. In Berkeley's form of idealism, all things are ideas. Physical objects, like chairs, trees, and rocks, are not made of matter. They are made of perceptions, what we see, hear, touch, smell, or taste. And those perceptions exist only in the minds that perceive them. If no mind perceives something, then it does not exist in any meaningful way. Suppose you leave your house for the day. Is your house still there while you're gone? Most people say yes. Berkeley says no, at least not in the way people think. He says your house continues to exist because God is always perceiving everything. For Berkeley, God is not a figure watching from far away. God is the ever-present mind that keeps the world in being by perceiving it. This sounds strange, so let's break it down. Berkeley did not deny that the world feels stable or regular. You walk into the same house each evening. You see the same furniture in the same place. You trust that your kitchen doesn't vanish when you're in the living room. Berkeley agreed with that. He just disagreed about what the world is made of. He said the world is not made of stuff that exists on its own. It is made of stable ideas kept in place by God's perception. To support this, he argued against the idea of material substance. Material substance is the concept of a thing that exists independently of anyone's mind. Berkeley said we never experience such a thing. When we say table, what do we mean? We mean something hard, flat, brown, maybe cold to the touch. All of these are sensations, ideas in the mind. We never get beyond them to some hidden material thing. Berkeley asked, why should we believe in a material world we cannot see or touch when everything we do see or touch is already in our mind? He also argued that the idea of matter causes more problems than it solves. Philosophers who believe in matter often have to explain how our ideas match the outside world. They worry about whether we are being tricked. Berkeley avoids this by removing matter from the picture. There is no gap between what we perceive and what exists. What we perceive is what exists. Let's say you see a red apple. You taste its sweetness and feel its weight. Berkeley says the apple is not a thing behind those sensations. The apple is the collection of those sensations. The apple is the taste, the color, the smell, the shape, all ideas in your mind. If no one perceives the apple, it ceases to exist in any full way. But it doesn't just blink out of reality. God continues to perceive the apple, so it remains stable and present in the world. Someone might object and say, what about when I close my eyes and walk away? Doesn't the apple still exist? Berkeley would answer that the apple exists in God's perception. In his view, this is not a weak answer. It is a strong explanation for why the world stays orderly. God's constant perception ensures that everything stays as it should, even when no humans are watching. Berkeley also believed this view protects us from skepticism. Skepticism is the idea that we might be wrong about everything we see. What if we live in a dream? What if a trickster is feeding us false ideas? Berkeley thought his version of idealism solved this. Since all we ever experience are ideas, and since ideas exist in minds, we have no reason to worry about being tricked by some unseen material world. We live in a world of ideas supported by a reliable and active mind, God's mind. He applied this thinking to science as well. He didn't reject science or math. He believed that laws of nature describe how ideas appear in regular patterns. When you drop a stone, you expect it to fall. This pattern is not caused by a hidden force in matter. It's part of the regular way God organizes perceptions. Gravity, in this view, is not a force between chunks of matter. It's a rule about how ideas behave in relation to one another. Let's imagine two people. One believes in matter, the other follows Berkeley. Both see a cat sleeping on a couch. The first says the cat is a material object. The second says the cat is a set of ideas in their mind. If the cat runs away and hides, the first person says the cat still exists somewhere as a physical thing. The second says the cat exists in God's mind until it returns to their view. Both people live in the same world. They both feed the cat and clean the couch, but they explain the world in different ways. Berkeley also pointed out that we never experience matter without perception. No one has ever seen an object without light. No one has ever touched something without feeling. So why insist there's something beyond perception when all our evidence comes from it? He thought it was simpler to say that perception is all there is. Some critics say this makes the world too dependent on the mind. What if minds disappear? Berkeley replies that God's mind never disappears. That means the world never stops existing. God's perception guarantees the stability of everything. For Berkeley, this is not only logical, it also aligns with his belief in a spiritual and active universe. Berkeley's idealism challenges how we think about reality. It asks us to set aside the idea of a world made of mindless matter. It replaces that with a world full of ideas, shaped and kept alive by an ever-present mind. In this view, seeing is not believing. Seeing is being, and being depends not on matter, but on perception. Imagine you walk into a room and see a chair. You touch it. You feel its shape. You hear your footsteps on the floor. It seems obvious that the chair and the room exist, even if no one else is there. But for George Berkeley, an Irish philosopher from the 1700s, this idea is mistaken. He argued that things do not exist outside of perception. In simple terms, he believed that to be is to be perceived. This view is called idealism. In Berkeley's form of idealism, all things are ideas. Physical objects like chairs, trees, and rocks are not made of matter. They are made of perceptions, what we see, hear, touch, smell, or taste. And those perceptions exist only in the minds that perceive them. If no mind perceives something, then it does not exist in any meaningful way. Suppose you leave your house for the day. Is your house still there while you're gone? Most people say yes. Berkeley says no, at least not in the way people think. He says your house continues to exist because God is always perceiving everything. For Berkeley, God is not a figure watching from far away. God is the ever-present mind that keeps the world in being by perceiving it. This sounds strange, so let's break it down. Berkeley did not deny that the world feels stable or regular. You walk into the same house each evening. You see the same furniture in the same place. You trust that your kitchen doesn't vanish when you're in the living room. Berkeley agreed with that. He just disagreed about what the world is made of. He said the world is not made of stuff that exists on its own. It is made of stable ideas kept in place by God's perception. To support this, he argued against the idea of material substance. Material substance is the concept of a thing that exists independently of anyone's mind. Berkeley said we never experience such a thing. When we say table, what do we mean? We mean something hard, flat, brown, maybe cold to the touch. All of these are sensations, ideas in the mind. We never get beyond them to some hidden material thing. Berkeley asked, Why should we believe in a material world we cannot see or touch, when everything we do see or touch is already in our mind? He also argued that the idea of matter causes more problems than it solves. Philosophers who believe in matter often have to explain how our ideas match the outside world. They worry about whether we are being tricked. Berkeley avoids this by removing matter from the picture. There is no gap between what we perceive and what exists. What we perceive is what exists. Let's say you see a red apple. You taste its sweetness and feel its weight. Berkeley says the apple is not a thing behind those sensations. The apple is the collection of those sensations. The apple is the taste, the color, the smell, the shape, all ideas in your mind. If no one perceives the apple, it ceases to exist in any full way. But it doesn't just blink out of reality. God continues to perceive the apple, so it remains stable and present in the world. Someone might object and say, "What about when I close my eyes and walk away? Doesn't the apple still exist?" Berkeley would answer that the apple exists in God's perception. In his view, this is not a weak answer. It is a strong explanation for why the world stays orderly. God's constant perception ensures that everything stays as it should, even when no humans are watching. Berkeley also believed this view protects us from skepticism. Skepticism is the idea that we might be wrong about everything we see. What if we live in a dream? What if a trickster is feeding us false ideas? Berkeley thought his version of idealism solved this. Since all we ever experience are ideas, and since ideas exist in minds, we have no reason to worry about being tricked by some unseen material world. We live in a world of ideas supported by a reliable and active mind, God's mind. He applied this thinking to science as well. He didn't reject science or math. He believed that laws of nature describe how ideas appear in regular patterns. When you drop a stone, you expect it to fall. This pattern is not caused by a hidden force in matter. It's part of the regular way God organizes perceptions. Gravity, in this view, is not a force between chunks of matter. It's a rule about how ideas behave in relation to one another. Let's imagine two people. One believes in matter, the other follows Berkeley. Both see a cat sleeping on a couch. The first says the cat is a material object. The second says the cat is a set of ideas in their mind. If the cat runs away and hides, the first person says the cat still exists somewhere as a physical thing. The second says the cat exists in God's mind until it returns to their view. Both people live in the same world. They both feed the cat and clean the couch, but they explain the world in different ways. Berkeley also pointed out that we never experience matter without perception. No one has ever seen an object without light. No one has ever touched something without feeling. So why insist there's something beyond perception when all our evidence comes from it? He thought it was simpler to say that perception is all there is. Some critics say this makes the world too dependent on the mind. What if minds disappear? Berkeley replies that God's mind never disappears. That means the world never stops existing. God's perception guarantees the stability of everything. For Berkeley, this is not only logical, it also aligns with his belief in a spiritual and active universe. Berkeley's idealism challenges how we think about reality. It asks us to set aside the idea of a world made of mindless matter. It replaces that with a world full of ideas, shaped and kept alive by an ever-present mind. In this view, seeing is not believing. Seeing is being, and being depends not on matter, but on perception. Picture sitting in a chair, reading this. You feel the weight of your body. You see the text. The world around you seems solid and real. Now ask a simple question. How do you know this world is not a simulation? The simulation hypothesis says that everything you see, touch, and think could be part of a computer program. You, your memories, the stars, these could all be data inside a system built by someone else. This idea may sound strange, but it rests on a clear line of reasoning. If it becomes possible to create conscious beings in a simulation, and if people build many such simulations, then it becomes more likely that we are in one of them, not in the original world. This comes from a thought experiment by philosopher Nick Bostrom. He offered 3 main points. First, humans may never reach the point where they can run simulations of conscious beings. Second, even if they can, they may choose not to. Third, if they do run many simulations, then the number of simulated minds would be far greater than the number of original minds. In that case, it becomes more likely we are in a simulation. Suppose future humans develop computers that can simulate a full world. Inside that world, beings think they are real. They ask questions, build machines, and even write books about philosophy. They don't know they're in a simulation because their world seems complete. If those future humans run many such simulations, each with billions of minds, then the total number of simulated minds could be immense. From a basic math point of view, if the number of simulated minds far exceeds the number of original minds, then any random observer is more likely to be one of the simulated ones. That includes you. Some people ask if simulated beings could really be conscious. Today, most simulations, like video games, run on basic rules. Characters follow scripts. They don't think. But if computing power grows, then future systems could model brains in fine detail. A brain is made of neurons firing in patterns. If those patterns can be simulated, then the same thoughts, feelings, and memories might arise. Think of a brain as a machine made of parts. If you can copy each part and its behavior in software, then the machine's function might stay the same. If the software version responds in the same way, recalls the same events, and makes the same choices, then what difference does it make whether it runs on neurons or on code? The idea does not need to assume anything magical. It only assumes that consciousness follows from information processing. If so, then a system that processes the same information in the same way should produce the same awareness. Let's imagine a simple case. A future lab creates a virtual world. In it, weather systems evolve, plants grow, animals roam. Then one day, conscious agents appear. They build tools, study the sky, and start to ask where they came from. Their world seems natural, but from outside, it's just a complex simulation, managed by someone else. If this is possible, then it raises the chance that we are in the same position. Everything we call physical, the air, the oceans, the laws of motion, could be part of the code. Even our own bodies and minds could be made of digital rules. In that case, the speed of light could be a processing limit. Quantum randomness could be the result of limited resolution. Space itself might be like the grid of pixels on a screen, fine enough to seem smooth, but not truly continuous. This doesn't mean the world is fake. It means it could be real at a different level. To a person inside the simulation, the world is all they know. A fire still burns. A fall still hurts. Emotions still arise. The experience is real, even if the cause is virtual. Some ask how we would know if we're in a simulation. There's no clear test. If the simulation is well made, it will avoid obvious errors, but small signs might leak through. Maybe we notice strange limits, places where physics behaves oddly. Maybe certain events seem too perfect or too rare to be natural. Maybe patterns appear that don't match expected randomness. Others point to the limits of computing power. Could a system run a world as complex as ours? The answer depends on the resources of the simulator. Our own computers grow more powerful every year. A far future society might harness entire stars to run simulations. If they exist, their systems could model many Earth-like worlds, each with billions of thinking agents. This leads to another point: motive. Why would anyone run such a simulation? One reason might be research. A simulator might want to study social change, language growth, or the spread of disease. Another reason might be curiosity. Like children building sandcastles, future minds might create worlds just to see what happens. The people inside those worlds would never know for sure. They might build their own simulations, unaware of how deep the chain goes. A mind inside a simulation could live a full life, with joy, loss, learning, and wonder, and never sense the outer layer. Some fear this means nothing matters. But that depends on how you define meaning. If your experiences feel real, then they are real for you. Whether you are made of atoms or code, pain still feels like pain. Love still feels like love. A simulated sunset can still move someone to tears. Others argue that the hypothesis cannot be tested, and so it belongs outside science. That may be true, but its strength lies in its logic. It asks us to think through what is possible, not just what we can measure today. As computing power increases, the question grows sharper. If we know that we can build realistic simulations, and if we choose to do so, then we must face the possibility that others already have. If we become simulators, we must consider that we were simulated first. In that sense, the simulation hypothesis is not about proving we live in a virtual world. It's about seeing the full scope of what a world can be, whether we find evidence or not. The idea challenges the line between what is natural and what is made. It reminds us that even the most basic facts, space, time, matter, may not be as fixed as they seem. Imagine you touch a hot stove. Your hand pulls back right away. At the same time, you feel pain. But ask yourself this: did the feeling of pain cause your hand to move? Or did the hand move first and the pain just followed? Epiphenomenalism says that the pain didn't cause anything. It was just along for the ride. Epiphenomenalism is a view in the philosophy of mind. It says mental states like thoughts, feelings, and sensations are caused by physical events in the brain. But they do not cause anything in return. Your body and brain act on their own, and the mind is just a byproduct, like steam coming off a train. The steam is real, but it doesn't make the train move. Take another example. You see a bear. Your heart races. You run away. Epiphenomenalism says your brain sees the bear, sends signals through the nervous system, speeds up your heart, and triggers your legs to run. You also feel fear, but your fear did not cause you to run. It came from the same brain activity that caused the movement, but it didn't play a part in making it happen. This idea goes against how most people think about their minds. We tend to believe our thoughts and feelings make us act. If you decide to eat an apple, it seems like your choice caused your hand to reach for it. But epiphenomenalism says the brain already started the process. The decision was just a mental shadow of that physical event. The view grew stronger in the 19th century when scientists began to see the brain as a physical machine. Reflexes, muscle movements, and sensory input all followed physical laws. The more we learned about nerves and brain signals, the more some thinkers wondered if the mind was needed at all. Maybe everything we do has a physical cause. In that case, what role does the mind play? Thomas Huxley gave a famous example. He said that mental states are like the whistle of a steam engine. The whistle tells us the engine is working, but it doesn't make it move. In the same way, feelings may show us that the brain is active, but they don't guide the body. They come after the action starts. This can sound troubling. If our thoughts don't cause anything, then are we just passengers in our own lives? Epiphenomenalism says yes. In a sense, the body acts. The brain triggers those actions. The mind watches, feels, and reflects, but it does not steer. Let's break it down further. Suppose you stub your toe. A nerve in your foot sends a signal to your spinal cord and up to your brain. The brain reacts. Your body jumps back. A moment later, you feel a sharp pain. You might say the pain made you hop away, but the reaction happened before you felt anything. The pain followed the action. According to epiphenomenalism, it had no role in causing the motion. Think about reflexes. When a doctor taps your knee, your leg kicks out. You don't choose that action. The signal doesn't even reach your brain at first. It loops through the spinal cord and back to the muscle. The brain finds out after the fact. That's a clear case where the mind plays no role. Epiphenomenalists say this may be true more often than we realize, even in actions we think are deliberate. One challenge to this view is that it seems to make the mind useless. If thoughts don't cause actions, then why do we have them? Why did evolution keep them around? Some thinkers say the mind helps us reflect and learn. Even if it doesn't cause behavior, it might help us remember patterns or understand mistakes. But others say this still assumes mental states can affect behavior, which epiphenomenalism denies. There are also problems with explaining how we talk about thoughts. If mental states don't cause anything, then how do we talk about them? How do we describe them in speech or writing? Saying, "I feel angry," seems to show that anger caused the words. But epiphenomenalists would say the brain activity caused both the feeling and the speech. The feeling did not lead to the words. The brain did both, and the mind just came along. Another problem is introspection. When you sit quietly and think, it feels like your thoughts lead to new thoughts. It seems like one idea causes the next. But epiphenomenalism says that brain activity is moving things forward. The feeling of one thought causing another is just part of the show, not the real engine. Some critics say the view is self-defeating. If beliefs don't cause actions, then how can anyone believe in epiphenomenalism because of reasons? If reasons don't cause beliefs, then people hold this view not because of logic, but because of physical brain states. Epiphenomenalists reply that this is true for all beliefs. We think we use reasons, but the belief forms because of brain processes. The reasons come later, as an afterthought. Others worry the view takes away human freedom. If thoughts don't guide actions, then choice becomes an illusion. We feel like we decide, but our brain made the choice before we knew it. The mind reports the choice, but didn't make it. That's a hard idea to accept, because we want to believe we are agents of our own lives. Still, some thinkers defend the view. They say it fits with what we know about the body. They argue that adding mental causes to physical ones creates problems. If every event in the body already has a physical cause, why add another? Epiphenomenalism keeps the system clean. The mind is real, but it does no work. It mirrors what the body does. Imagine a lighthouse with a spinning light. As the light turns, it sweeps across the ocean. The ship sees the beam, but the beam doesn't move the light. It just shows where it's pointing. In the same way, mental states show what the brain is doing. They do not guide it. This view is hard to test. We can't measure mental states without using behavior, and behavior may not reflect cause. So the debate remains open. But the idea keeps returning. Each time we learn more about how the brain works, the same question comes up. What role, if any, does the mind really play? Epiphenomenalism answers that question with a quiet but firm claim. The mind exists, it feels, it watches, but it does not act. Imagine standing on the edge of a black hole. You watch as light bends, time slows, and anything that crosses the boundary, the event horizon, can never escape. Now imagine the entire universe as a black hole, not inside one, not near one. The universe itself is a black hole. This idea is not just science fiction. Some physicists have explored this possibility using real equations and models from general relativity and quantum theory. The key is understanding what makes a black hole a black hole. It's not just that it sucks things in. It's that it traps everything inside a certain boundary. That boundary is called the event horizon. Nothing that crosses it can come back, not even light. A black hole forms when a huge amount of mass gets squeezed into a small space. If enough matter collapses into a single region, gravity becomes so strong that escape becomes impossible. But gravity isn't only about objects like stars or planets. gravity also curves space itself. And the more mass there is, the more space curves. Now, think about the universe. It has mass, it has energy, it has a size, though that size keeps changing. If you take the total mass and energy of the universe and plug those values into the equations for a black hole, something interesting happens. The universe seems to match the basic properties of a black hole. Black holes have a size called the Schwarzschild radius. That's the distance from the center of a mass where the event horizon would form. If all the mass of the universe is within that radius, then it would count as a black hole. Calculations show that the size of the observable universe is close to its Schwarzschild radius. That means, from an outside point of view, if such a point existed, our universe might look exactly like a black hole. Of course, there's a problem. We can't see outside the universe. We don't know if there is an outside. Everything you can observe is inside our cosmic horizon. That's the farthest light can travel since the beginning of time. So if our universe has an event horizon, we are inside it. That's what black holes do. They trap regions of space. And from our position inside, we can't tell if the outer edge is really an event horizon or just a limit of what we can see. There's another angle to this idea. Some theories suggest that what we call the Big Bang, the start of the universe, might be connected to the collapse of matter into a black hole somewhere else. Instead of thinking of a black hole as a dead end, think of it as a bridge. Some physicists call this a white hole. A white hole is the opposite of a black hole. Nothing can go into it, and everything comes out. If a black hole traps matter, a white hole spits it back out. Some models show that when a black hole forms, a new region of space-time might open on the other side. That new region could expand, just like our universe does. Imagine a star collapsing into a black hole in another universe. As it compresses, the matter reaches an extreme point. At that moment, it could spark the beginning of another universe on the other side, a white hole explosion that creates new space, new time, and new laws of physics. From that perspective, our universe could be the interior of a black hole formed in some parent universe. What looks like the Big Bang to us might be the bounce of matter collapsing elsewhere. This kind of model helps solve a few puzzles. One is the question of where the energy for the universe came from. If it came from a black hole in another space-time region, then the energy was never created from nothing. It was transformed. Another puzzle is why the universe looks so uniform in all directions. If it grew from a very small region inside a black hole, then that region would be compressed and smoothed by the extreme gravity, explaining the even spread of matter. Another interesting idea comes from the holographic principle. This principle says that the information inside a volume of space can be stored on the surface of that space. It's like how a hologram works. A two-dimensional surface holds all the data needed to show a three-dimensional image. For black holes, this means the contents inside the event horizon might be described by data on the horizon itself. Some physicists think the same is true for our universe. The information about everything we see, galaxies, particles, light, might be stored on the boundary of the universe, not inside it. If that's true, then the entire universe might be a kind of hologram. And if that boundary is like the event horizon of a black hole, the link becomes even stronger. One of the most detailed black hole models is the Kerr black hole. This type spins and has a ring-shaped singularity instead of a point. Some studies show that space-time near a spinning black hole could allow for other universes to exist on the far side. These universes would be cut off from ours by the event horizon, but inside the black hole, the direction of time flips. Space becomes time, and time becomes space. That strange shift might make expansion possible, like the rapid growth we see in our universe after the Big Bang. We can't travel into a black hole to test these ideas, but we can use math and physics to simulate them. When researchers do that, they find that the inside of a black hole can, under certain conditions, behave a lot like the early universe. Rapid expansion, high energy, and a clear boundary between regions of space, all these features match. Even the way time flows in the universe fits this model. In a black hole, time slows near the edge. From the outside, a falling object seems frozen at the horizon. But from the inside, time feels normal. That's how our universe feels too. To an outside observer, again, if one existed, we might appear to slow as we approach the edge of our cosmic horizon. But for us, time ticks along normally. That's what you'd expect from being inside a giant black hole. This doesn't mean the universe is doomed to collapse. Some black holes grow instead of shrink. If the universe is a black hole, it might be the kind that expands from the inside out, driven by its own gravity and energy. From our point of view, that looks like cosmic expansion. From another angle, it could be matter falling inward forever toward a center we will never reach. The models are not complete. They raise new questions as they try to answer old ones. But the idea that the universe could be the inside of a black hole is one of the rare cases where imagination and the mathematics agree. It turns the structure of space inside out. What looks like a distant future, an expanding universe, might actually be the echo of a collapse that happened long ago, somewhere beyond our reach. Imagine you drop a glass. It hits the floor, shatters, and spreads shards in every direction. You know the cause, the drop, came before the effect, the break. That's how the world seems to work. Causes lead to effects. The future doesn't change the past. But some ideas in physics suggest that this might not be the whole story. Retrocausality is the idea that the future can influence the past. At first, this sounds impossible. How can something that hasn't happened yet affect something that already did? But in quantum mechanics, the rules are not as fixed as they seem. When particles behave in strange and unpredictable ways, some physicists ask whether future events might play a role in shaping what happens now. Start with a basic idea from quantum theory. When we measure a particle, we affect it. Imagine you drop a glass. It hits the floor, shatters, and spreads shards in every direction. You know the cause, the drop, came before the effect, the break. That's how the world seems to work. Causes lead to effects. The future doesn't change the past. But some ideas in physics suggest that this might not be the whole story. Retrocausality is the idea that the future can influence the past. At first, this sounds impossible. How can something that hasn't happened yet affect something that already did? But in quantum mechanics, the rules are not as fixed as they seem. When particles behave in strange and unpredictable ways, some physicists ask whether future events might play a role in shaping what happens now. Start with a basic idea from quantum theory. When we measure a particle, we affect it. Before the measurement, a particle like an electron does not have a definite position or spin. It exists in a range of possible states. Once we measure it, the wave function collapses, and we get one result. But what decides which result we see? One answer is chance. Another is hidden variables, factors we don't yet understand. A third, less common view is retrocausality. In this view, the result depends not only on what happened before the measurement, but also on what happens after. To understand how this might work, consider the delayed choice experiment. This idea comes from physicist John Wheeler. In the classic double-slit experiment, particles like photons or electrons go through two slits and form an interference pattern. That pattern shows wave behavior. But if we place detectors at the slits to check which slit each particle goes through, the interference disappears. The particles act like little balls, not waves. In Wheeler's delayed choice version, we decide whether to measure which slit the particle went through only after it has passed through the slits, but before it hits the screen. Strangely, the result seems to depend on our late decision. If we measure the path, the particle acts like a particle. If we don't, it acts like a wave. It's as if the choice we make in the present decides how the particle behaved in the past. This leads some physicists to suggest that future choices may reach backward in time to shape earlier events. Retrocausality doesn't mean we can rewrite history in big ways. It means that under very specific rules, future events might play a role in how past quantum states settle. Another example comes from experiments with entangled particles. When two particles are entangled, measuring one instantly affects the state of the other, even if they are far apart. This is called non-locality. It looks like the effect travels faster than light, which breaks the rule that nothing can go faster than light. Some researchers ask whether retrocausality could explain this. Maybe instead of the effect moving through space, the future measurement sends a signal backward in time to the moment when the particles were entangled. That change then ripples forward to the second particle. In this view, both outcomes are linked through time, not space. That avoids the need for faster-than-light communication. Think of it like this. Two friends each flip a coin. The coins always land on opposite sides. If one is heads, the other is tails. It looks like one coin knows what the other did. But what if their flips are not just linked in space, but also in time? What if the result of one slip travels backward to the shared moment of setup, and then forward again to the other flip? This sounds like science fiction, but in quantum math, it's not easy to say which direction time flows. The equations work the same way forward and backward. Time symmetry means that if you reverse time in the equations, they still make sense. This is not true for most everyday processes, like melting ice or growing older. But in quantum theory, time does not clearly point in one direction. That opens the door to the idea that events in the future could help determine how the past plays out, especially when no one has observed the outcome yet. Retrocausality doesn't say the future always shapes the past. It says that in specific, carefully defined situations, the two might be linked in both directions. Some theories, like the two-state vector formalism, build on this. In that model, the state of a particle is described by two wave functions, one coming from the past and one coming from the future. These wave functions meet in the middle. What we observe depends on both. This doesn't mean the future is fixed. It means that past and future work together to produce the outcome. One reason physicists explore retrocausality is to solve certain puzzles in quantum theory. For example, Bell's theorem says that if local hidden variables exist, they can't explain the results of entanglement. That means we have to give up something, either locality, realism, or the forward-only flow of time. Retrocausality offers a way to keep locality and realism by allowing time to go both ways at the quantum level. Still, the idea has critics. Most physicists prefer models that keep causes before effects. That fits better with our everyday experience. Others point out that retrocausality could create paradoxes. If you could send a signal to the past, could you change it? Could you stop the signal from being sent? That would cause a contradiction, but in the quantum version, these kinds of paradoxes may not arise. The effects are limited to small, carefully structured systems. They do not let you send a message or prevent a known outcome. To picture how this might work, think about a crossword puzzle. When you solve one clue, it can help you solve another. Imagine walking into a room and seeing a chair, a table, and a lamp. You point to each and say, "That's a thing." This seems obvious, But ontological nihilism says something else. There are no things. Nothing exists in the way we usually think it does. According to this view, objects do not exist as separate entities. The world has no furniture, just arrangement, structure, or raw material without parts. Ontological nihilism belongs to a branch of philosophy called metaphysics. Metaphysics asks what exists and what it means for something to exist. Most people assume that tables, trees, animals, and people are real, separate things. Ontological nihilists reject that. They argue that the world contains no composite objects, no things made of parts. If you think you see a table, what you're really seeing is a group of particles arranged table-wise. But there is no table as a separate entity above that arrangement. To understand this, start with the idea of composition. Composition is the process by which smaller parts combine to make a larger whole. For example, legs and a flat surface make a table. Cells make a body. Bricks make a wall. Most people believe that when parts come together in the right way, a new thing exists, the whole object. But ontological nihilism says this step never happens. There are only the parts, never the wholes. This view is strict. It doesn't say some things are illusions. It says all composite objects are. The only things that exist are the smallest, indivisible parts, whatever those turn out to be. These might be particles, fields, or something even more basic. But the key point is this: if something has parts, it doesn't exist as a thing. The parts do, the whole does not. Take a simple example. You look at a pile of sand. Common sense says the pile is a thing. But the nihilist says no, it's just many grains in a certain arrangement. The pile doesn't add anything to the picture. It's not a new object. It's just a way of speaking about how the grains sit. When you remove the grains, you don't find a leftover pile floating in space. So the pile itself was never real. This idea also applies to complex systems. Think about a car. It has wheels, an engine, a frame. You use it every day. But ontological nihilism says that car is just a label. What exists is a set of parts, each with its own place and function. A car is not a thing over and above those parts. We call it a car for convenience, but there's nothing in the world called a car. There are only atoms in car-like arrangements. Even people don't escape this view. A person seems like a single entity, but we're made of cells, which are made of molecules, which are made of atoms. If a person has parts, then by nihilist standards, a person doesn't exist as a whole. The body is an arrangement, the mind is a process. Neither is a new object formed from parts. Each is a system, but systems are not things. They are patterns in how parts behave. You might wonder how this differs from saying that objects are just concepts. But ontological nihilism is not idealism. It does not say the world is made of ideas. It says the world is real, but composed only of simples, parts without parts. The mistake is thinking that groups of simples form new objects. A nihilist says that is like seeing shapes in clouds. The shapes are not there, we project them. Suppose someone builds a robot. They bolt the pieces together. They turn on the power. The robot moves. Most people would say they've created a new object. But the nihilist says the builder just rearranged particles. Nothing new was added. The robot is not a new entity. It's a complex pattern. The parts remain the only real pieces. The rest is language. This might sound like a word game, but there are reasons behind it. One reason is parsimony. In philosophy, parsimony means not multiplying entities without need. The fewer types of things you claim exist, the simpler your theory. Ontological nihilism follows this principle. It removes all composite objects from the list. Only simples stay. This gives the cleanest ontology, one with the fewest assumptions. Another reason is identity. If you believe in composite objects, you must answer hard questions. When does a group of parts become a new thing? If you remove one part from a chair, is it still the same chair? What if you replace every part over time? Is it still the same object? These puzzles, like the ship of Theseus, show how vague the idea of composition can be. Nihilism avoids these problems by denying that composition creates new things in the first place. This view also matches certain physics models. At the smallest scale, physics doesn't find chairs or trees. It finds particles, fields, or mathematical structures. Larger objects don't appear in the equations. They emerge as patterns. So some philosophers say ontological nihilism reflects what science already shows, that everyday objects are not part of the fundamental picture. There are challenges. Language is one. We talk in terms of objects. We say, "This is a cup," or "I parked the car." Ontological nihilism says these ways of speaking are useful but false. They help us navigate the world, but do not describe its true structure. That makes the theory hard to live by, even if it's logically sound. Another challenge is practical. If only simples exist, can we still do science, law, or ethics? Can we have rights if people don't exist? Can we own things that aren't real? A nihilist answer is that these fields work because of shared language and agreed rules, not because the objects are real. You don't need real chairs to talk about sitting. You just need a shared idea of what sitting means. Ontological nihilism does not deny reality. It says reality is different from how we usually describe it. The world exists, the parts exist, but what we call objects are only mental tools. They help us group parts and predict behavior. They are not extra things. Think of it like this. You draw a square on paper. The square seems like a new shape, but really, it's just 4 lines. The square doesn't exist apart from them. It's how they meet. The lines are real. The square is a structure. That's how ontological nihilism sees all objects, as nothing more than arrangements of parts, never things in their own right. Imagine holding a credit card with a hologram. Tilt it, and you see a 3-dimensional image. That image has depth, but it's stored on a flat surface. The holographic principle says something similar might be true for the universe itself. What we see as a 3-dimensional world could be a projection from information stored on a distant 2-dimensional boundary. The idea came from black hole physics. In the 1970s, physicist Jacob Bekenstein found that a black hole's entropy, its measure of disorder, scales with its surface area, not its volume. This was strange. For most things, entropy grows with volume. A bigger box can hold more disorder. But a black hole's entropy increases only with the size of its event horizon, the surface that marks its boundary. Stephen Hawking later showed that black holes also give off radiation, now called Hawking radiation. That meant black holes could shrink and vanish, raising a problem. If the black hole disappears, what happens to the information about what fell in? This became known as the information paradox. In physics, information should not vanish. If you burn a book, the words become unreadable, but the information stays in the smoke, ash, and heat. If a black hole erases information, it breaks this rule. To solve the paradox, physicist Gerard 't Hooft and later Leonard Susskind proposed a new way to think about information and space. They suggested that everything inside a black hole might be fully described by data stored on its surface. In other words, the 3-dimensional contents are encoded on a 2-dimensional boundary. This is the holographic principle. The information in a volume of space can be described by information on its surface, like a hologram stores a 3D image on a flat film. This principle might apply to the entire universe, not just black holes. Suppose you imagine the universe as a sphere with a surface. The holographic principle says that everything happening inside the sphere, all the galaxies, stars, atoms, and even your thoughts, could be described by data on that surface. This doesn't mean the universe is fake. It means the deepest laws might work in 2 dimensions, even though we see 3. One major development came from string theory. In the late 1990s, physicist Juan Maldacena proposed a model where a type of gravity in a curved, five-dimensional space is exactly equal to a quantum field theory with no gravity on its flat, four-dimensional boundary. This result is called the ADS-CFT correspondence. It gives a working example of the holographic principle. The model uses a special kind of space called anti-de Sitter space, which is not the same as our universe, but it shows the idea can work in practice. In Maldacena's model, every event inside the five-dimensional space has a mirror in the four-dimensional surface theory. A particle falling into the deeper space corresponds to a change in the boundary. You can do all the math in the boundary theory and get the same answers you would in the bulk. This shocked many physicists. It suggested that gravity, space, and even time could be emergent, not fundamental, but built from deeper rules that live on a surface. To see how this might work, imagine a video game. You see a world with depth, motion, and space, but the real code sits on a flat storage chip. The game's 3D world comes from two-dimensional instructions. In the same way, the holographic principle says the laws of physics may come from information on a surface we can't see directly. This view challenges our ideas about space and matter. If the universe is holographic, then what we think of as distance or size might be illusions. Objects that seem far apart in space might be close together in the hidden, two-dimensional description. In quantum physics, particles can be entangled, linked in a way that seems to break normal space. If two particles are entangled, changing one affects the other instantly, no matter how far apart they are. In a holographic view, their connection might be local in the surface theory, even if it looks distant in space. Some researchers use this idea to study quantum gravity. Gravity and quantum mechanics are hard to unite. General relativity describes gravity as curves in space-time, while quantum mechanics describes particles and forces as probabilities and fields. They work well on their own, but when you try to mix them, things fall apart. Black holes are the main place where both theories matter, so they act as testing grounds. The holographic principle gives one way to build a gravity theory from quantum rules on a lower dimensional surface. That could be a step toward a full theory of quantum gravity. People also explore how this applies to cosmology. Our universe doesn't have the same shape as anti-de Sitter space, but some models try to use holographic tools anyway. They ask whether the Big Bang, dark energy, or inflation could be explained by boundary theories. It's not easy, because the math is complex and the spaces are different. But the goal is to learn if the universe we live in has a simpler description on a lower dimensional surface. Even if we can't see the boundary, the math suggests it could still exist. Just like you can't see the hologram film while watching the image, we may never detect the boundary directly. But if the holographic principle is true, then all events, all objects, and all forces, including you, could be encoded on that surface. This changes how we think about location, size, and even identity. In normal physics, a person is a body in space. In holographic terms, a person is a patch of data on a distant surface, projected inward as a living being. That being feels space, walks through rooms, and sees stars, all as part of a 3D display built from lower dimensional rules. The principle doesn't claim that our experiences are fake. It claims that the ultimate description of the world may not use the space we live in. The space could be real to us, but made from something deeper. It's like the difference between a printed book and the file that created it. The book is real, but the file holds the source. This view also brings limits. In a normal region of space, you might expect that you can store as much information as the volume allows. But the holographic principle says the limit is set by the surface area. That means there's less room for information than we thought. It also suggests that information is never lost, even in black holes. The surface always keeps the record, even if the details vanish from sight. Not all physicists accept the principle in full. Some think it only applies in certain cases. Others see it as a powerful tool, but not yet a full theory. Still, it gives a new way to think about old problems. If the world is a projection, then what we see may not be all there is, but it may still be enough to learn the truth. Imagine standing at a train station. You see a train arriving. A moment later, you see people stepping off. Then the train leaves. These events seem to happen in order. First arrival, then stopping, then departure. That feels like time moving. But in 1908, philosopher J.M.E. McTaggart argued that time does not move. In fact, he claimed that time is not real at all. He didn't mean clocks are broken or that we can't measure intervals. He meant that time, as we understand it, past, present, and future, is an illusion. His argument is now called McTaggart's paradox. It challenges how we think about change, events, and the passage of time. McTaggart began by breaking time into two ways of describing events. He called one the A series and the other the B series. The A series describes events as past, present, or future. For example, you might say, the meeting was yesterday, the train is here now, and dinner will happen later. This is how people usually talk about time. It changes. The future becomes the present, and the present becomes the past. The B series, on the other hand, arranges events by their position in a timeline. One event comes before or after another. You say, the meeting happened before the train arrived, or dinner comes after the train leaves. These facts don't change. If the meeting was before the train yesterday, it still is today. The order stays the same. Only the A series involves change. McTaggart said that if time is real, then change must be real too. And change only exists in the A series. The B series just gives a fixed order. It doesn't explain motion, growth, or becoming. If we remove the A series, we remove change. And if we remove change, we remove time. So far, that might seem fine. We just say the A series is what gives us time. But McTaggart claimed the A series is flawed. He said it leads to contradiction. To explain why, consider an event like a birthday. Let's say your birthday is next week. That means it is in the future. After some days pass, it becomes the present. Then, when it ends, it becomes the past. McTaggart said, we now have a problem. The birthday has all three properties. It is future, present, and past. But that seems impossible. An event can't be all three at once. It is future, it hasn't happened. If it is present, it is happening. If it is past, it has already happened. These properties are exclusive. Something can't have them all at once. You might respond that the birthday has these properties at different times. It is future on Monday, present on Sunday, past on Tuesday. That seems to save the day. But McTaggart said this only delays the problem. Now you need to say, the birthday is future at Monday, present at Sunday, past at Tuesday. But this new move uses time again. You are now describing when the birthday has its A series properties. That means you are applying the A series a second time. You're saying the event was future, then present, then past, each at a different moment. But each of those moments now also needs to be described using A series terms. That creates a loop. You must apply the A series again and again to explain the first A series. This leads to what McTaggart called an infinite regress. There is no final explanation for how events change from future to present to past. Each attempt to define that change just pushes the problem back. Because of this, he concluded that the A series is incoherent. If the A series is incoherent and the B series doesn't provide real change, then time itself can't be real. This idea seems to clash with how we live. We feel time passing. We remember the past. We expect the future. We watch clocks move and days unfold. But McTaggart said this is a mistake. Our sense of time is part of how we experience things, not how the world really is. The events of the world may just be laid out, fixed in their order, with no real flow from one to the next. To see this another way, imagine a long film strip. Each frame shows a moment: a man walking, a glass falling, a bird flying. When you play the film, it looks like time moves, but each frame is just sitting there. The movement comes from how you watch the strip, not from the strip itself. McTaggart thought the universe might be like that. The events are there, arranged in sequence, but the passage of time is something we add. This raises questions about memory and experience. If time isn't real, then what are we doing when we remember something? McTaggart might say we're just located at a part of the sequence where certain mental events happen. In one part, you have the memory of an earlier event. That gives the illusion that something has changed. But really, the events and the memories are fixed. There is no movement between them. Some philosophers disagreed. They said we don't need to say events are future, present, and past all at once. We just need to say they occur in that order. They argued that the B series is enough. Time doesn't need to flow to be real, just needs to have structure. As long as events happen in a consistent order, earlier and later, then time exists. McTaggart insisted that order without change is not real time. He said real time must include becoming, and that becoming only exists in the flawed A series. Others tried to explain the problem using tense logic. They argued that the birthday doesn't have all the properties at once. It has them at different times. And this doesn't create a contradiction. But McTaggart's point was deeper. He wasn't just saying the properties conflict. He was saying that explaining their shift from one to another always requires more shifts with no clear end. That, he thought, shows the structure fails. Even today, this argument still sparks debate. Some think McTaggart misunderstood the nature of time. Others think he uncovered a deep problem with how we explain change. Some scientists even say physics agrees with him. In relativity, time is just another dimension, like space. Events are fixed. The past, present, and future all exist. Time doesn't flow, it just is. In that view, we are like readers moving through a book. The pages are already written. We read one after another, and that gives the feeling of motion. But the story was already there. The events were already set. If that's true, then maybe McTaggart was right. Time, as we think of it, may not exist. We just experience it that way, frame by frame, one illusion at a time.
Imagine laying out a strip of film. Each frame shows a single moment. One frame shows a person walking. The next shows them taking another step. Another shows them standing still. These frames do not move. They just sit in order on the strip. But when you play them fast enough, they create the illusion of motion. The block universe theory says that reality is like this film strip. Every moment in time, past, present, and future, exists all at once. Time does not pass. We only experience it that way. In physics, this idea comes from the theory of relativity. In 1905, Albert Einstein showed that time is not separate from space. They are part of a single structure, space-time. In everyday life, space and time seem different. You can move through space in any direction, but time seems to move only forward. Relativity changes this view. It shows that space and time mix together. Movement through time depends on movement through space. More importantly, it shows that different observers can disagree on what events happen at the same time. Imagine two people, far apart, watching a supernova explode. One person is moving toward the star. The other is moving away. According to relativity, they will disagree on when the explosion happens. For one, it might be now. For the other, it might be in the future. That means the idea of now is not absolute. There is no single, universal present moment that everyone shares. Instead, each person has their own slice of time, depending on their motion. This challenges our usual sense of time. We think of the present as real, the past as gone, and the future as not yet. But if different people disagree on which events are present, then what makes one moment more real than another? The block universe says none is more real. They are all equally real, laid out in a four-dimensional structure. Past, present, and future are just locations in space-time. Think of a mountain range. Each peak is a different height. None is more real than the others. They all exist, even if you can only stand on one at a time. The block universe treats moments in time like this. Each one exists in the structure. You experience only one at a time, but the others are still there. This model helps explain how time works in relativity. Events are points in space-time. Their order depends on your path through that space-time. Some events are fixed in order. One always comes before the other. Others can switch, depending on your frame of reference. This flexibility suggests that time is not something that flows. Instead, it is a dimension you move through, like a road. Now picture your own life. You were born, learned to walk, went to school, and now sit reading this. In the block universe, all those moments still exist. You at age 5 is a point in space-time. You reading this is another. Your future self, asleep in bed or walking outside, is another point. None of these moments vanishes. They all remain part of the structure. Your experience of one moment does not erase the others. The feeling of time passing comes from your mind moving along the time axis. You remember past events and expect future ones, so it seems like time flows. But in this model, your brain simply exists in different states at different points in space-time. Memory is a feature of those states. You remember the past because the structure includes a version of you with those memories. Some scientists use this model to study the laws of physics. The block universe fits well with equations that treat time like a dimension. In many physical laws, time works the same forward and backward. That means the laws do not care which direction time goes. If you record a video of 2 billiard balls hitting each other and play it backward, the motion still makes sense. The laws hold either way. This symmetry supports the idea that time does not flow, it just is. You can also think about light cones. In space-time diagrams, light cones show which events can affect each other. The past light cone includes all events that can reach a point through light or slower signals. The future light cone includes all events that the point can influence. Events outside the cone are elsewhere. In the block universe, all these events are fixed. You can trace the cone, but nothing inside or outside the cone disappears. The structure contains it all. This view also shifts how we think about change. In everyday life, we think change happens because time moves. But in the block universe, change is a difference between locations in space-time. One point has a red leaf. Another point has a green leaf. One point has a person standing. Another has the person sitting. Change is not a process. It is variation across the structure. It also changes how we think about free will. If the future already exists, does that mean our choices are fixed? Some say yes. If all moments are set, then your decision to read this was already in the structure. Others say you still make choices. They are just part of what the structure includes. The fact that your decisions are recorded does not mean they were not made. You can compare this to a map. A city map shows all the roads and buildings. Your path through the city is fixed once you take it. But as you move, it feels like you are choosing which way to go. The map exists whether you've walked it or not. The block universe treats time the same way. The structure includes every path. Your movement through it creates the experience of choice. This model also fits with some interpretations of quantum mechanics. In some views, all possible outcomes of a quantum event exist in different parts of the structure. You see one outcome, but the others are still there. just in other branches or regions. The block universe can hold all these outcomes without needing time to move or collapse. For most people, this idea feels strange. It doesn't match how we live. We feel time pass. We feel that the future is open and the past is closed. But feelings are not facts. The block universe suggests that time is like space. We move through it. We remember some parts. We forget others. But the parts do not vanish. They are there, fixed, in the structure of the universe. Imagine a flat metal plate. You sprinkle fine sand on it. Then you run a violin bow along the edge. The sand jumps and moves. Soon it forms clear shapes, circles, grids, or stars. These patterns are not random. They depend on the vibration of the plate. Change the sound, and the pattern changes. This is cymatics, the study of visible sound and vibration. Cymatics shows how sound can shape matter. When sound waves pass through a surface, they create pressure points. The sand moves away from high-pressure areas and settles in low-pressure zones. The result is a pattern that reflects the sound's frequency and shape. Low tones make simple shapes. Higher tones make more complex ones. The effect is repeatable and precise. The idea is not new. In the 1600s, Galileo noted that sand would shift into patterns on a vibrating surface. In the 1700s, German scientist Ernst Chladni developed the technique further. He used metal plates and violin bows to create repeatable sound figures, now called Chladni patterns. In the 20th century, Swiss doctor Hans Jenny gave the field its name. He used speakers, fluids, and powders to show how vibration affects matter. These experiments raise a question. If sound can organize sand, can it also organize other things? What if vibration plays a deeper role in shaping the world? In physics, waves are everywhere. Light is a wave. Sound is a wave. Electrons behave like waves under certain conditions. Even space-time, according to general relativity, can ripple in the form of gravitational waves. This raises the possibility that vibration, or structured oscillation, is not just a surface effect, but part of how nature works at every level. Think of atoms. They are not solid balls. They are mostly empty space, with particles in motion. These particles vibrate. They form structures, like molecules and crystals, based on the way they interact. If you think of particles as points in a vibrating field, then matter itself may be a kind of standing wave, a stable pattern formed by motion. In string theory, this idea becomes central. The theory proposes that the most basic units of matter are not particles, but tiny vibrating strings. Each type of particle corresponds to a different vibration mode. A photon is one mode, an electron is another. The properties of the particle, like its mass or charge, depend on how the string vibrates. Though unproven, string theory brings cymatics into the realm of fundamental physics. If the theory is correct, then vibration is not just an effect. It is the source of all particles and forces. Take another example, the early universe. In the first moments after the Big Bang, the universe was dense and hot. Tiny ripples, small variations in energy, spread through space. These ripples became the seeds for galaxies and stars. In this way, early sound-like waves shaped the structure of the cosmos. We still see their imprint in the cosmic microwave background, a faint glow left over from the early universe. Even biology shows signs of vibration-based organization. Inside the body, cells use rhythmic pulses to communicate. The heart beats, neurons fire in waves. The brain produces patterns of electrical activity, alpha waves, beta waves, and more. These rhythms are not noise. They are structured and meaningful. Disruption in these patterns often points to illness or imbalance. In embryos, certain cell layers fold and form body structures, partly through mechanical waves, vibrations at the cellular level. Sound also affects larger systems. When sound passes through water, it creates shapes. Vibrations cause air or fluid to flow in new ways. Researchers have used sound to move particles, control droplets, and even guide the growth of tissues. These effects are not magic. They follow physical laws, but they suggest that sound is more than a signal. It can be a tool for shaping structure. Consider how music affects people. Sound waves from speakers enter the ear, move tiny hairs, trigger neurons, and create emotion. That emotional response can lead to movement, thought, or even healing. Music therapy uses this principle to help people with brain injuries or mood disorders. The body responds to rhythm, tone, and vibration in deep ways. These effects are complex, but they point to the body's sensitivity to vibrational input. In some systems, resonance plays a key role. When something vibrates at its natural frequency, it absorbs more energy. A swing pushed at the right moment goes higher. A glass exposed to a matching tone may shatter. In the same way, cells and tissues may respond most strongly to certain frequencies. Researchers study how specific tones affect cells, slowing growth, triggering repair, or changing behavior. Though results vary, the interest in using sound to affect biology continues to grow. In practical terms, cymatics remains a visual demonstration. You can make patterns with simple tools: a metal plate, a speaker, some powder. But the deeper question is whether these patterns reflect a principle that extends beyond the lab. Do vibrations underlie the forms we see in nature? Are objects shaped not only by material forces, but also by hidden rhythms? If we look at snowflakes, shells, and leaves, we see repeated shapes: spirals, hexagons, branching forms. These patterns arise from energy flows, pressure, and vibration. They are not drawn by hand. They emerge from how forces interact over time. In this way, nature builds complex shapes from simple rules. Vibration may be one of those rules. Some researchers ask whether space itself has a frequency. If the vacuum is not empty, but a field, then it may have properties we don't yet understand. Quantum fields fluctuate, even in empty space. If those fluctuations form stable patterns, they may give rise to particles, just as sound forms patterns in sand. In that case, what we call a particle may be a stable note in a vast vibrational field. This does not mean sound creates everything. It means vibration, as a general feature of systems, may be central to how things come to be. Cymatics shows us this in simple, clear form. Sound shapes matter into order. That order reflects frequency and structure. It's not proof of a grand theory, but it opens the door to thinking of vibration not just as a result, but as a cause. When we see patterns in the world, we might ask not just what made them, but what shaped them, and whether vibration played a role. Imagine building a robot that acts like a person. It walks, talks, responds to questions, and shows emotion on its face. Now ask a harder question. Does it know what it's doing? Does it feel anything? Or is it just simulating the behavior of a conscious being without being conscious itself? The simulation of consciousness is the idea that we might create machines or systems that appear to be aware but are not. They copy the outward signs of consciousness: speech, emotion, decision-making, but have no real inner experience. Understanding this idea means thinking about what consciousness is, how we might model it, and whether a simulation can become the thing it imitates. Consciousness is the state of being aware. It includes having thoughts, feelings, sensations, and a sense of self. You know when you are in pain. You know you are reading this sentence. These are not things you guess. They are direct parts of your experience. That inner life is hard to measure from the outside, which makes it difficult to tell if another system, like a machine, has it. Some argue that you can simulate all the behaviors of consciousness without creating true awareness. A system might be trained to say, "I feel sad," when certain conditions are met. It might adjust its actions based on that state, but saying the words and feeling the emotion are not the same. In this view, the machine is a good actor. It plays the role of a person, but nothing is happening inside. Others think that consciousness comes from structure and function. If you build a system that processes information in the right way, then it will become conscious. In this view, there is no magic moment. You don't need a soul or a special spark. You just need the right kind of processing. A brain does it with neurons. A machine might do it with circuits or software. To see the difference, think about a weather simulation. You can model a storm on a computer. The wind, rain, and pressure all change on screen, but the simulation does not get wet. It shows the storm, but it is not the storm. The question is whether consciousness is like weather. Can you simulate it without producing the real thing? Or is it something that comes with the process? Now consider how the brain works. The brain receives signals, processes them, and sends outputs. When you touch a hot stove, your skin sends a signal to your spinal cord and brain. You pull your hand back. At the same time, you feel pain. That pain is not just a signal, it is a conscious state. It is something it feels like to be you in that moment. Suppose you build a machine that copies every step of that process. It senses heat. It processes the signal. It withdraws. It says, ouch. The system acts just like a person, but is it aware? Is there a feeling inside the machine? Or is it just reacting without any inner life? Some researchers say this depends on how the system is built. If it has the same complexity and feedback loops as a brain, then maybe it has real consciousness. If it only copies the surface behavior, then it does not. A chatbot that answers questions might seem smart, but it doesn't have beliefs or memories, unless those are built into its structure in a way that supports awareness. Think of a mirror. It reflects your face. It matches your movements. But the mirror does not understand what it shows. A simple chatbot might be like that, reflecting patterns without knowing anything. A more complex system might build its own model of the world. It might have a sense of its own state. It might be able to think about itself. Some people say that's what matters. If a system can model itself, then it is on the path to real awareness. There's also the question of intent. When you speak, you have a reason. You choose your words. If a machine copies your speech, but without intent, is it conscious? Some say no. Others say that intent itself is just another process. If the machine forms goals and adjusts its behavior to meet them, then maybe it does have intent, even if it is not human. Another approach looks at information. One theory says that consciousness is a property of systems that process information in certain ways, called integrated information theory. It says that if a system has enough complexity and connection between parts, it becomes conscious. This idea gives a possible test. You could measure how much integration exists in a system. If the score is high, the system is likely conscious. If not, it's probably just simulating. Still, measuring inner states from the outside is hard. You can't look at a machine and know if it feels anything. You can only judge by behavior, structure, and internal complexity. That means we might create systems that act conscious without knowing if they are. Some researchers test this with thought experiments. One is the Chinese room. Imagine a person inside a room. They don't speak Chinese, but they have a rule book that lets them match symbols. When someone slides a Chinese sentence into the room, they follow the rules and send back a proper reply. To an outside observer, it seems like the person inside understands Chinese, but they don't. They're just following patterns. This suggests that simulating language is not the same as understanding. The system acts right, but has no grasp of meaning. Critics of this example say that while the person doesn't understand, the whole system, the person and rulebook together, might. Supporters say true understanding needs more than pattern matching. Another challenge comes from uploading minds. If you scan a brain and recreate it in software, will that copy be conscious? It might act like the person. It might remember their life, their fears, their hopes. But is it aware, or just a shadow of the original? If it is conscious, does the person still live on in the copy? These questions matter if we ever build systems that act like people. If a machine claims to suffer, do we believe it? If it asks for rights, do we listen? If it doesn't feel anything, we can treat it like a tool. If it does, then we face hard ethical choices. The simulation of consciousness asks where the line is between real and fake awareness. Can we build machines that only act awake, or can we make ones that truly are? Is consciousness a special substance, or just a kind of pattern? The answers remain unclear, but the question keeps growing more urgent as machines get closer to crossing that line. Imagine sitting in a room. You see a chair, hear the hum of a fan, feel the floor under your feet. These are your experiences. Now ask yourself, what proof do you have that anything outside these experiences exists? Can you be sure the chair is real? That the fan is there? That the room exists when you stop noticing it? Phenomenal solipsism starts from these questions. It says your own conscious experience is the only thing you can know for sure. This idea is not about being selfish or self-centered. It is a philosophical position about knowledge and existence. It says that nothing exists beyond your own stream of awareness. You might see people, hear voices, read books, and talk with others, but all of that happens inside your experience. You never step outside your own mind, so you can't confirm that anything else exists at all. This is different from standard solipsism, which claims that only the self exists. Phenomenal solipsism does not claim that the world isn't real. It says that if anything else exists, you can't know it. All you can truly know is the contents of your own consciousness, what you see, hear, think, and feel. Think about a dream. While you sleep, everything in the dream seems real. You walk through a city, talk with people, eat food. It all feels solid. But when you wake up, you realize it was all in your mind. Phenomenal solipsism asks, how do you know you're not dreaming now? Not in the usual way, but in the deeper sense that your entire world is part of your private experience. Say you meet a friend at a cafe. You see them smile. You hear them talk. You laugh together. But all of that happens in your field of awareness. You experience a version of them, how they look and sound to you. You never step into their mind. You assume they have thoughts and feelings, but you don't experience those directly. You construct the idea of their mind based on behavior, but that idea is still part of your own experience. This is what phenomenal solipsism points out. Everything you know comes through your own consciousness. Your memory, your senses, your thoughts, all of it takes place within your own point of view. There is no neutral outside position you can step into. You can't compare your experience to reality itself. You only ever have access to what appears to you. This doesn't mean the world is fake. It means that the concept of a world, including the idea of fake or real, is something you experience. It is part of your mental life. It may correspond to something outside your awareness, but you have no direct proof of that. You can only guess. Imagine looking at a tree. You see green leaves, rough bark, light and shadow. These are your perceptions. You believe the tree is there, but you can't get outside your perception to confirm it. Even if you walk around the tree or touch it, you are still within your experience. Everything you know about the tree is shaped by your mind, your senses, your brain, your thoughts. Phenomenal solipsism builds on this. It says all claims about the world depend on experience. Without experience, there is no access to anything. So from your own position, your conscious life is the entire field of certainty. Anything else, even your own body, is known only through how it appears to you. You might ask, what about science? Doesn't it give us objective facts? But science depends on observation and measurement. You read results in books, see data on screens, Hear others explain theories. All of that still comes through your awareness. You can believe the data points to an outside world, but you only encounter that data in your own experience. Suppose you stub your toe. You feel pain. That pain is not an idea or a theory. It's a direct, vivid part of your consciousness. But the toe itself, the floor, the cause, those are ideas you connect to the pain. You never feel the toe as a thing in itself. You feel a cluster of sensations and give them a name. Phenomenal solipsism says the sensation is certain. The rest is belief. Some argue that this position leads to isolation, but it doesn't deny the presence of other people in your experience. You still see faces, hear voices, feel touched by others. What it questions is whether these people exist outside of your awareness. They might, but since you only ever know them as parts of your experience, you can't confirm they exist independently. You might think this is just a trick of words, but the point is not to confuse. It is to make clear what you can and can't know. You can know how things appear to you. You can know your feelings and thoughts. You can know how the world seems. But the source of that world, whether it is physical, virtual, or something else, is not open to direct inspection. Even your own sense of self is part of this field. You think thoughts. You feel like someone is having those thoughts. But that someone is also part of the picture. You experience a sense of being you. That sense is real in your awareness, but it doesn't prove there is a self beyond the stream of thought and feeling. This view doesn't tell you to stop acting in the world. You still get hungry, walk, speak, plan, and care. But it shifts how you see what you're acting in. Instead of assuming a world out there, you see everything as part of a lived experience, one that may or may not reflect something beyond it. It also raises deep questions about knowledge. What does it mean to know something? If knowing means being able to describe or predict, then you can still know things within your experience. You can know patterns, changes, causes, and effects as they appear. But if knowing means reaching outside your experience to something beyond, then phenomenal solipsism says you can't do that. This idea doesn't tell you what the world is. It tells you where your limits are. You know experience. You don't know what, if anything, lies behind it. All the rest, objects, people, time, space, appears within that experience. Whether they exist on their own is a question you can't answer from inside the experience itself. Imagine you're choosing what to eat for dinner. You pick pasta, but you wonder, could you have picked something else? Maybe you almost picked rice. That kind of thought is common. We think about what could have happened, what might happen, and what must happen. These are modal ideas, ways the world could be, not just how it is. David Lewis, a philosopher from the 20th century, took these thoughts seriously. He said that when we talk about possibilities, we talk about real things. For Lewis, every way the world could be is a way that some world actually is. This view is called modal realism. According to it, possible worlds are just as real as the actual world. They are not made up or imagined. They are full, concrete worlds, just as solid and detailed as our own. The only difference is that we live in this one. The rest exist elsewhere with their own objects, laws, and events. Each world is isolated from the others. No one in one world can visit or interact with anyone in another, but they are all equally real. To understand this, think about the phrase, "It's possible that it will rain tomorrow." In modal realism, that claim is true if there is a world just like ours up to today, where it rains tomorrow. When you say, "I could have worn a red shirt instead of blue," you mean that in some other world, a world that branched off at your morning choice, you wore red. In that world, you live a slightly different version of your day. Maybe no one notices. Maybe someone compliments you. That world is real, according to Lewis. Each world contains its own people, objects, and events. You have a counterpart in many of them. That counterpart is not you. It is a person much like you, living a similar life but not the same life. When you say, "I might have become a musician," modal realism says that's true if in another world your counterpart became one. You didn't, but someone who is a lot like you did. This helps explain how we use modal language. We often say things like, "It's possible that," or "It could have been," or "It must be the case that." Lewis's theory gives these statements a clear truth condition. Possible means true in some world. Necessary means true in all worlds. Impossible means true in no worlds. Instead of treating these as vague ideas, modal realism treats them as claims about a vast collection of real, detailed worlds. This approach makes logical systems of possibility simpler. In standard modal logic, we talk about possible worlds as abstract tools. They help us evaluate truth in different scenarios. But Lewis argued that these tools work so well because they reflect something real. Rather than say they are useful fictions, he said they are real places. Their usefulness comes from their existence. Critics of modal realism often raise the same question first. Isn't this too strange? Do we really want to believe in an infinite number of other worlds? Lewis agreed it was strange. He called it a philosophical cost, but he said the gain was worth it. Modal realism explains modal talk in a simple and uniform way. Other theories, like treating possible worlds as sets of statements or ideas, can't do the same work without extra complexity or exceptions. Lewis believed the best theory is the one that explains the most with the fewest moving parts. For him, that was modal realism. Let's look at an example. Imagine a coin flip. It lands heads, but you think it could have landed tails. Under modal realism, that means there is a world where the exact same coin, under the same conditions, landed tails instead. The physics worked out differently, perhaps due to tiny changes we can't detect. That world exists. You don't live in it, but someone just like you does. In that world, maybe your mood changed, or your day went a little differently. Modal realism also helps with counterfactuals. These are statements like, "If I had left earlier, I would have caught the bus." To evaluate that, you imagine a world where you left earlier. You look at what happens next. In modal realism, that world is not just a mental image. It is a real world where your counterpart left early and caught the bus. The truth of the statement depends on what happens in that world. Lewis used the idea of similarity to compare worlds. When we think about what could have happened, we look for the closest possible world where it does. Closest means most similar to ours in relevant ways. If you say, "If it had rained, the game would have been canceled," you imagine a world like ours in all respects, except with rain. And you check whether the game was canceled there. The closer the world, the better the fit. You might wonder how these other worlds exist. Are they in space? Do they float somewhere? Lewis said no. They are not far away. They are separate in a deep way. No space, time, or causation connects them to us. Each world is a complete, standalone universe. It has its own space-time, its own objects, and its own events. We can't see them or travel to them. We only refer to them when we talk about what could be. This sounds radical, but Lewis compared it to other cases in science. Think of atoms. For centuries, people couldn't see them, but they helped explain observations. Over time, evidence grew. Lewis thought modal realism might be the same. We don't see other worlds, but the theory helps us understand logic, language, and possibility. Still, many philosophers reject modal realism. Some say it violates common sense. Others say it multiplies entities without need. Why believe in countless unseen worlds when we can explain modal talk with ideas or models? Lewis responded that common sense can be wrong. And even if modal realism is expensive, It might be the only theory that pays its own way by explaining possibility in full detail. Lewis didn't claim that modal realism is easy to accept, but he said that if we already believe in other times and places, like distant planets or past centuries, then other worlds are just more of the same. They are just as real, but unreachable. We don't see all of space or time, yet we believe in it. The same can be true for possible worlds. For Lewis, taking possibility seriously means taking all possibilities as real, not as ideas, not as models, but as fully formed worlds. Our world is one among many. What makes it actual is simply that we live in it. It is not more real. It is just the one we call home.
Imagine waking up in a quiet room. You look around. You see a bed, a window, and a clock. You feel the blanket on your skin. You hear a bird outside. Everything seems normal. But you pause and ask, how do I know any of this is real? How do I know the world exists outside my own mind? Solipsism starts with that question. It is the idea that only your own mind is certain to exist. Everything else, people, objects, places, might not be real. They might be parts of your experience, but not things that exist on their own. You see a tree, you feel the wind, but those things could be images or sensations inside your mind. There might be no tree, no wind, no world. You might be the only conscious being that exists. Solipsism is not a belief that the world is fake on purpose. It is not a claim that someone is tricking you. It does not say the world is imaginary in the way dreams are. Instead, it says that you cannot know whether anything exists beyond your experience. The question is not what exists. The question is what you can know with full certainty. Solipsism starts from a strict view of knowledge and builds from there. You know you think. You feel pain, joy, hunger, and doubt. You might wonder if you're wrong about something, but you can't be wrong that you are thinking. That's the core idea in Descartes' famous phrase, I think, therefore I am. The fact that you can doubt proves that something is doing the doubting. That something is your mind. This is the one thing you can't deny. Everything else depends on it. Now imagine walking through a city. You see cars, people, lights, and signs. You smell food. You hear traffic. These all seem real, but each is part of your private experience. You assume they come from an outside world, but you have no direct proof. You see colors, hear sounds, feel textures, but all of these are in your awareness. You don't see the objects themselves. You see what they look like to you. Suppose you speak with a friend. They laugh and tell a story. You respond. You both share memories. But all of this, what they say, how they look, the sound of their voice, happens within your awareness. You assume they have a mind like yours, but you never see their thoughts. You never step into their mind. You only observe behavior. You connect that behavior to your own experience of thinking and feeling. But that is still a guess. This leads to a key part of solipsism. You can't confirm that other minds exist. You can talk to people. You can watch them cry or smile. But all of that might be part of how your own mind works. Maybe your brain, or whatever you are, is generating this world with these people. They seem to act like you. They seem to have feelings. But that does not prove they are conscious. It only proves that they appear to be. In philosophy, this is known as the problem of other minds. You can never know another mind from the inside. You only see the outside. In daily life, we trust that others think and feel. But solipsism says that trust is based on habit, not certainty. We treat others as real, but we don't know they are. This also applies to the physical world. When you touch a rock, you feel resistance. When you taste fruit, you register sweetness. But all of these are mental events. They happen in you. You assume they come from outside.
but that is a story you tell yourself. You never get outside your mind to compare experience with some external thing. So solipsism holds that even the idea of a physical world is uncertain. Now think about a movie. You watch it. You feel suspense, joy, fear. But you know the movie isn't happening in real life. You know it's a set of images and sounds. Solipsism asks, how do you know your whole life isn't like that? Not fake, but all part of an internal process. You don't have to believe it's a dream. You only have to accept that you can't be sure it's not. This does not mean solipsism claims the world is false, or that you are in control of it. It doesn't say you are creating everything on purpose. It only says that you cannot know anything beyond your own conscious state. You can have beliefs about the world. You can build theories, but none of those beliefs can be fully proven. Some people think solipsism is absurd because it leads to extreme isolation. If only you exist, what's the point of talking or acting? But solipsism is not a guide to behavior. It is a limit on what you can claim to know. You can still care about others. You can still enjoy life. You just recognize that all of it happens within your experience, and that's all you truly have access to. Others argue that solipsism is self-refuting. If you say, only I exist, then you've already used language, ideas, and meanings that depend on others. You've learned words from people. You use logic built by thinkers. So even the claim of solipsism assumes more than solipsism allows. But the solipsist replies that this is part of the point. All these things, words, ideas, people, are part of their experience. That's all they claim. They don't say those things are false. They say they can't prove they are more than contents of their own mind. Solipsism can be hard to accept, not because it's wrong, but because it feels strange. We grow up thinking of the world as shared. We talk, learn, and live with others. The idea that all of that might be inside one mind seems unnatural. But strange doesn't mean false. It only means it challenges what we take for granted. You don't need to believe in solipsism to see its value. It pushes you to ask hard questions. How do I know what I know? What is the source of my belief in the world? Can I trust my senses? These are not just abstract thoughts. They shape how you see reality. Solipsism shows that even the most basic things, your body, your friends, your surroundings, depend on your experience of them. That's where all knowledge begins. Whether it goes beyond that is a question that solipsism leaves open. Imagine a triangle. It has 3 sides, and the angles always add up to 180 degrees. This is not just true on paper. It's true in every math class, in every country, at every time. Now ask a deeper question. What if everything, including space, time, matter, and even you, is like that triangle? What if the universe is not just described by math, but is math? That's the idea behind the mathematical universe hypothesis. It comes from physicist Max Tegmark. He suggests that the universe is not made of stuff sitting inside space. Instead, the universe is a mathematical structure. The particles, the forces, the laws, they don't just follow math. They are math. To understand this, start with how physics works. We use math to describe the world. Newton's laws use equations to predict how objects move. Einstein's theory of relativity uses geometry to describe gravity. Quantum mechanics uses math to explain how particles behave. These equations work with great precision. They describe the motion of planets and the flow of electricity. They match what we see. Most scientists see this as a tool. The math describes reality, but the universe itself is made of matter and energy. Tegmark goes further. He says that if math works so well, maybe it's not just a tool. Maybe it's the thing itself. Imagine a cube in geometry. It has edges, corners, and faces. Those features are fixed by the math. You don't need wood or plastic to have a cube. The cube exists as a shape. Tegmark says the universe might be like that, an abstract structure that exists in the same way a cube exists. It just happens to feel real because we are part of it. This view starts from a bold idea. If a mathematical structure is logically possible, then it exists in the same way our universe does. So there's not just one math-based universe. There are many. Each possible set of equations gives rise to its own universe. Ours is just one of them. We live in the one that supports observers like us. Think of all the equations you've seen. Some describe curves, others describe waves, others describe spaces with different shapes. If each set of rules describes a complete world, then the collection of all such rules describes a vast multiverse. Each world runs its own math, its own physics, and its own version of reality. Most are not fit for life, but some are, and we find ourselves in one of those. This helps explain a puzzle in physics. Why do the laws of nature have the values they do? Why is gravity so weak? Why do electrons have the mass they have? These numbers seem finely tuned. If they were different, stars would not form, atoms would not hold together, and life would not exist. One answer is luck. Another is design. Tegmark offers a third: selection. If all possible mathematical universes exist, we find ourselves in one that supports life, because we couldn't exist in the others. Now imagine you are a character inside a computer game. The world around you follows rules: gravity, time, energy. You live, act, and think based on those rules. From your view, the world is real. But from the outside, it's all code. The rules are not applied to the game. They are the game. The game is the math. Tegmark's idea is similar, but without the need for a computer. The universe doesn't run on math. It is math. This also changes how we think about objects. In a normal view, a table is made of atoms. Those atoms follow rules, which we describe with equations. In Tegmark's view, the table is a collection of mathematical relationships. The atoms are patterns in a structure. Even space and time are not places where math happens. They are part of the structure itself. A point in space is not a dot floating somewhere. It's a set of relations to other points. You might ask what math means in this view. It's not numbers written on a board. It's not symbols in a textbook. It's the set of logical structures that exist whether or not anyone sees them. A square exists in geometry, even if no one draws it. It has properties like symmetry and area. Tegmark says the universe is the same. It exists as a structure with defined rules, independent of human thought. This idea ties to the role of observers. We are part of the structure. Our thoughts, our senses, our theories, they are internal features of the math. Just as a spiral is part of a shell, our minds are patterns in the overall system. Our awareness is not added to the structure. It arises from it. The structure has parts that feel, remember, and question their own nature. Some scientists object. They say that math is a language, not a thing. We use it to model the world, but that doesn't make the world mathematical. Others say that not all math describes something real. Some equations are beautiful but useless. Why should we believe that every possible set of math rules leads to a real universe? Tegmark answers that the boundary between physical and abstract may not exist. If a structure is consistent and complete, it exists in the same sense that our universe does. The only difference is perspective. We see our structure from the inside, so it seems real. Other structures feel the same way to whatever is inside them. He also points to simplicity. The hypothesis explains why math works in physics. It explains why the laws seem fine-tuned. It doesn't need extra rules or assumptions. It just says, all math is real, and we are part of one piece of it. This leads to a final step. If the universe is a mathematical structure, then the search for truth is a search for the right description of that structure. Physics becomes the task of identifying which math we are part of. Each discovery, whether it's a new particle, a new symmetry, or a new constant, is a clue to the larger pattern. In that sense, the mathematical universe hypothesis is not just a claim about reality. It is a way to see the world. It treats nature not as a machine, but as a pattern. Not as a stage, but as a statement. Not as a thing, but as a relationship. It invites us to understand not just what exists, but why its form is the way it is, and whether that form is the same as truth itself. Imagine waking up in a hospital room. You look around and recognize the walls, the light, and the smell of antiseptic. You recall who you are, how you got there, and what happened yesterday. You assume the room was there all along, even while you were unconscious. But what if the room, the light, and everything in it depends on your awareness? That's the core idea behind biocentrism. Consciousness does not arise from the universe. The universe arises from consciousness. Biocentrism is a theory developed by Robert Lanza. It says that life and consciousness are not the result of matter. Instead, matter and the universe result from consciousness. This flips the usual view. In most models, the universe came first, billions of years ago, and life evolved later. In biocentrism, awareness is the base layer, and everything else, space, time, objects, comes from it. The argument begins with a simple point. You never experience anything without consciousness. Every color, sound, shape, and smell appears in your awareness. Even time and space only show up inside your mind. You don't see time itself. You notice change. You remember what happened and anticipate what might happen. But you never see the past or future directly. You live in a stream of now. Suppose you look at a red apple. You call it red because of the way it appears in your mind. But the apple itself does not contain redness. The color is how your brain interprets certain wavelengths of light. If you had different eyes or a different brain, the apple might not look red at all. This means that what we call reality is shaped by the structure of the observer. The apple exists in your experience, but the form it takes depends on how you observe it. Biocentrism goes further. It says that without observation, reality does not settle into a definite form. This idea echoes quantum physics. In certain experiments, particles act like waves until someone measures them. Only then do they take on a clear position or path. Until that moment, they exist in a state of probability. The famous double-slit experiment shows this well. Light behaves like a wave when not observed, but acts like a particle when measured. The outcome seems to depend on whether someone is watching. Some physicists explain this using the concept of the observer effect. The act of measurement changes the system, but biocentrism suggests something deeper, that observation is what gives reality its shape in the first place. Until a conscious mind engages with the world remains in a state of undefined potential. Think of a video game. Nothing on the screen is real in the usual sense. The world exists as code until the player moves into a new area. The graphics engine then builds what the player sees. In biocentrism, the universe might work the same way. The world around you forms as you become aware of it. It does not sit out there waiting to be found. It takes shape as part of the act of perception. This doesn't mean that reality is an illusion. It means that what we call the external world is bound to the act of awareness. The trees, the stars, and the mountains all exist, but they exist as experienced. You never step outside experience to check what they're like without a mind. You can only describe how they appear within your awareness. Now think about death. In a materialist view, consciousness ends when the brain shuts down. Awareness is a byproduct of chemical activity. When that activity stops, the mind goes dark. But if biocentrism is true, then consciousness is not tied to the brain. The brain is a tool, a structure within experience. but not the source of experience. Consciousness is the framework within which all things appear, including the brain. If this is correct, then death is not the end of awareness. It is a change in form. Just as space and time appear within consciousness, so does the sense of being a body in time. When the body stops working, that pattern ends, but the field of awareness remains. Biocentrism doesn't claim to know what happens after death, but it does suggest that consciousness does not vanish, because it was never a product of the body to begin with. Critics of biocentrism say it lacks hard proof. They point out that neuroscience shows clear links between brain activity and conscious states. Damage to parts of the brain changes how we think and feel. Drugs, injuries, and illness alter our sense of self. This suggests that the brain does produce awareness. Biocentrism responds that these changes do not prove the brain creates consciousness. They show that the brain shapes experience, but that's not the same thing. A broken radio distorts sound. It doesn't prove the radio creates the music. In the same way, the brain might be a receiver or filter of awareness, not its source. If you damage the filter, the signal gets scrambled, but the source might still be present. Biocentrism also asks why anything exists at all. Physics can describe the behavior of particles, but it can't explain why particles exist in the first place. It gives laws, but not origin. By putting consciousness first, biocentrism treats awareness as the starting point. Existence happens within consciousness, not the other way around. This also affects how we think about time. In most views, time is a backdrop. Events move from past to present to future. But you never see time itself. You see motion, change, and memory. Biocentrism says that time is part of experience. Without a mind to notice change, there is no past or future, only a timeless state of possibility. Time does not flow. The sense of flow is part of how awareness works. Space is similar. We treat space as a container. Things move through it, but space is also part of how we arrange perceptions. We don't see space itself. We see distance, shape, and motion within awareness. If you remove the observer, you remove the framework that allows for space. All of this may sound abstract, but it touches daily life. Every thought, every feeling, every object appears in your field of awareness. That awareness is not separate from the world. It is the world in the only form you ever know it. Biocentrism does not require you to believe in anything beyond experience. It only asks you to notice that experience is where everything begins. When you look at a tree, hear a voice, or feel cold air, you're not accessing a world beyond you. You are in contact with a world shaped through your awareness. That world may be shared, stable, and lawful, but it remains tied to the field of experience. In this view, life is not a product of the universe. The universe is a product of life. Imagine you wake up in a room and see that the walls, the air, and the light all seem just right. The temperature fits your body. The oxygen level is safe to breathe. The floor holds your weight. Everything seems made for you. But instead of asking why it is that way, you might ask how it could be any other way. If the room didn't support your life, you wouldn't be in it. That's the idea behind the anthropic principle. It starts with a simple fact: we are here. We observe the universe because it allows beings like us to exist. That means the universe must have the kinds of features that make life possible, at least in some part. If it didn't, we wouldn't be here to ask questions about it. This principle comes in different forms. The basic version is called the weak anthropic principle. It says that our observations of the universe are limited by the fact that we exist. We can only observe a universe that supports life. That sounds obvious, but it has real implications. It means we should not be surprised if the universe seems tuned to allow life. If it didn't, we wouldn't be here to notice. Imagine a fisherman who only catches fish longer than 6 inches because that's the size of the holes in his net. He wonders why all fish seem bigger than 6 inches. But the answer is simple. smaller ones slip through. His sampling method affects what he sees. In the same way, our existence affects what kind of universe we can see. The strong anthropic principle takes this further. It says the universe must have the properties that allow life to arise at some point. Some versions go even further and suggest that life is not just allowed, but required. These versions are more controversial because they seem to imply that the universe is made with life in mind. One reason the anthropic principle matters is that many features of the universe seem finely tuned. If some basic physical constants were slightly different, life as we know it could not exist. If gravity were stronger, stars would burn too fast. If it were weaker, stars might not form at all. If the electromagnetic force were much different, atoms wouldn't hold together. The same goes for the strength of the nuclear forces, the mass of particles, or the rate of cosmic expansion. Change any of these values even a little, and life becomes impossible. So why are the values just right? One answer is chance. Maybe there is only one universe, and it happens to have the right settings. But that seems unlikely to some scientists because the odds appear so small. Another answer is design. Maybe some force, power, or intelligence set the values to allow life. But this explanation brings its own questions and moves into areas beyond science. A third answer comes from the idea of a multiverse. If many universes exist, each with different values for the physical constants, then it's not surprising that one of them supports life. We live in one that does because we couldn't live in one that doesn't. The anthropic principle then becomes a filter. Out of all possible worlds, only those that support life can have observers. That's where we find ourselves, not because this universe is special, but because it is suitable. Imagine a vast field filled with bubbles. Each bubble is a universe. Most are empty, some collapse right away. A few last long enough for stars to form. Out of those, an even smaller number have the right balance for chemistry and biology. You find yourself in one of those rare bubbles, not because you picked it, but because only those bubbles allow for any kind of awareness. The anthropic principle helps explain why we find ourselves in a bubble that works. This principle also affects how we view time and space. The observable universe looks very large. It contains billions of galaxies, each with billions of stars. But the anthropic principle suggests that we shouldn't expect to find ourselves in an average place. We should expect to find ourselves in a place that allows life. That could be a rare spot in a much larger or more complex system. Just because something is rare doesn't mean it's unlikely to be observed, if it's the only place where observers can exist. In cosmology, the anthropic principle plays a role in explaining the age of the universe. The universe is about 13.8 billion years old. That might seem arbitrary, but it fits the time needed for life to develop. Stars had to form, burn, and explode to create heavy elements. Planets had to form from those elements. Life had to arise and evolve. The time we live in is not random. It is one of the few windows when the universe has cooled enough for life to exist, but hasn't grown too cold and dark yet. Some scientists use the principle to explain the size and shape of the universe. Others use it to help select among competing theories. If one theory predicts a universe that could not support life, and another predicts one that can, the second theory may be more likely, simply because we know life exists. This does not prove the second theory is right, but it may guide which models we take seriously. Critics say the anthropic principle is not an explanation at all. They argue that it's circular. We're here because we're here. But defenders say that the principle sets limits on what kinds of answers make sense. It does not explain why the universe exists. It explains why we see the kind of universe we do. Others say the principle can be misused. It's not a reason to stop asking questions. Saying the universe must allow life does not mean we should stop trying to understand how it works. But the principle can help us frame the questions better. It reminds us that any theory must account for the fact that observers exist. We are not outside the system, we are part of it. In the end, the anthropic principle is a boundary condition. It says any theory of the universe must allow for conscious life, or at least for observers. That's not the whole answer, but it is a starting point that shapes how we think about the rest. Imagine reading a book. The story describes a red apple sitting on a wooden table. You picture the apple in your mind. You can almost feel the smooth skin and see the shine of the surface. But is there really a red apple? In the book, yes, in the story, but not in the room. You are not looking at an object in the world. You are responding to a description. Anti-realism says the same thing might be true of much more than stories. It suggests that the things we talk about in science, ethics, and even daily life may not exist independently of our beliefs, perceptions, or language. Anti-realism is not one idea. It is a stance you can take in many areas. You can be an anti-realist about science, about values, about numbers, or about objects. What links all of these is a shared doubt, the idea that reality, as we talk about it, might not exist on its own. Instead, what we call real might depend on how we observe, describe, or use it. Start with science. A realist about science says that scientific theories aim to describe the world as it is, even the parts we can't see. If a theory talks about electrons, then real electrons exist. We may not observe them directly, but they are out there. Anti-realists don't agree. They say theories help us organize and predict what we observe, but that doesn't mean the unobserved parts are real. For example, when we say atoms have protons, neutrons, and electrons, we are describing a model. It works. It explains chemistry and electricity. But the anti-realist says that usefulness is not proof. The theory could work well even if the particles are not real in any deep sense. They are tools, not truths. This view becomes clearer with past theories. At one time, scientists believed in phlogiston, a substance that explained why things burned. It turned out to be wrong. Later, A believed in the ether, a medium through which light waves traveled. That also turned out to be false. An anti-realist looks at this history and says we should be cautious. Just because a theory works now does not mean its parts are real. Theories change, so do our ideas of what exists. Now, think about ethics. A moral realist says that right and wrong are real features of the world. An action is good or bad regardless of what anyone thinks. Killing an innocent person is wrong whether or not anyone says so. A moral anti-realist disagrees. They say moral values come from humans. We make judgments based on feelings, customs, or reasoning, but there are no moral facts out there. Morality is not found, it is created. That doesn't mean it's random. It means it depends on us. This matters in everyday life. When you say stealing is wrong, do you mean it is truly wrong in some deep, universal way? Or do you mean it violates a shared rule, one that people have agreed on? If you take the second view, you lean toward anti-realism. You still care about the rule. You still think people should follow it, but you don't say it reflects a built-in feature of the universe. In math, the question is whether numbers exist independently of us. A realist says that numbers are real objects, even if they are abstract. The number 2 exists, even if you can't touch it. It has properties. You can't change them. 2 + 2 = 4, no matter who you are. An anti-realist says numbers are part of a system we invented. They don't exist outside of rules and symbols. We agree on what they mean. We use them to build systems, but they are not part of the world like trees or stones. Consider a different kind of example. You see a rainbow in the sky. You know it forms from light passing through water. It looks like it has a clear shape and position, but try to find its location and it moves. You can't touch it or stand under it. In a way, it is real. You see it. But it's not an object you can hold. It's an effect of light, water, and your point of view. Anti-realists say many things are like this. They seem real, but their reality depends on how we observe and describe them. Some people think anti-realism is just skepticism, but it's not the same. Skepticism says we can't know what is real. Anti-realism says the concept of real depends on context. In science, it may depend on what a theory explains. In ethics, it may depend on what people value. In math, it may depend on what rules we accept. The anti-realist does not always say, nothing exists. They often say, we need to ask what we mean by exists. This shows up in language. Suppose you say, there is a hole in the shirt. What is a hole? It's not a thing on its own. It's an absence of fabric. But you talk about it as if it's an object. Language lets you treat it that way. An anti-realist pays attention to this. They ask whether the things we name are actually independent parts of the world, or just ways we talk about it. Now, take fiction. You say Sherlock Holmes lives at 221B Baker Street. That's true in the story, but Holmes doesn't exist. Still, we speak about him as if he does. The anti-realist notices that we do the same with other concepts, forces, numbers, values. We act like they exist to help us make sense of things, but they may not exist as separate entities. Anti-realism doesn't mean you stop doing science, making moral choices, or using math. It means you recognize that these systems may not point to an independent reality. They work because they fit our experience and needs. That makes them powerful, but it may not make them true in the deepest sense. The anti-realist sees knowledge as something made within a framework, not something dug out of a world that waits to be discovered. To hold this view is not to reject knowledge. It is to ask where knowledge comes from and what it tells us. If all our knowledge depends on tools like observation, language, and theory, then we should be careful before saying what is real. Anti-realism doesn't close the door. It just points out that the door is part of the house we built. Imagine turning off every light, every sound, and every movement in a room. You try to create a space with nothing in it. No heat, no motion, no matter. Even if you manage to remove everything you can detect, you still do not have a true vacuum. At the smallest level, something still moves. That something is the zero-point field. It's a background sea of energy that exists even in complete emptiness. It doesn't come from particles or waves in the usual sense. It's built into the structure of space itself. The zero-point field comes from quantum physics. In quantum theory, particles don't sit still. Even at their lowest energy state, called the ground state, they still fluctuate. These fluctuations are not caused by anything. They are built into the rules of quantum mechanics. The field never truly rests. Even at absolute zero, where all thermal motion stops, these quantum fluctuations remain. This means that space is not truly empty. It's filled with a subtle energy, the zero-point energy. Every point in space has this energy. It's not easy to detect because it doesn't produce heat or light, but its effects show up in precise experiments. One example is the Casimir effect. If you place two metal plates very close together in a vacuum, they attract each other. This happens because the zero-point field is slightly reduced between the plates. There are fewer allowed quantum fluctuations in that space. The difference in energy creates a tiny force that pushes the plates together. The field exists all around us and inside us. It's not made of particles flying around. It's more like a background hum in the structure of space-time. Some researchers ask whether this field could relate to consciousness. The idea is not that consciousness floats in the field or that the field itself is a mind. The idea is that the zero-point field might provide the conditions for consciousness to arise,
or even be a part of what consciousness is. One proposal is that the brain might interact with the zero-point field. The brain has billions of neurons. These neurons fire in patterns. The connections between them form complex networks. Some scientists think that these patterns might not just stay inside the brain. They might also influence or be influenced by the quantum vacuum. If true, the brain would not only be a biological machine, it would also act like a quantum antenna, tapping into a field that links everything. This is not the same as saying the brain is a quantum computer. Quantum computers use fragile states like superposition and entanglement, which are hard to maintain. Most brain activity can be explained without using quantum effects, but the idea here is different. It says that the background field might store or reflect information, and that the brain might access or modify this field in some way. To picture this, think of a lake. The brain is like a stone tossed into the lake. The ripples move outward. If you toss another stone in a different spot, the ripples interact. You can study the pattern to learn something about the stones. In this analogy, the zero-point field is the lake, and brain activity sends ripples through it. If many brains are doing this, then the field could hold a record of these patterns. Consciousness would not be a closed loop in one head. It would be part of a broader system. Another way to approach this is through information. In physics, information is conserved. It doesn't vanish, even if matter changes form. Some theories suggest that the zero-point field could store information about past states of systems. If the brain can read from or write to this field, then some aspects of memory or awareness might involve more than the brain itself. This idea could also explain why consciousness feels unified. The brain handles many processes at once. You see, hear, move, and think all at the same time. Yet your sense of self is single and continuous. If the brain uses a field that spans all space, then the unity of awareness might come from that shared background, instead of binding everything inside your head. The mind might bind through a deeper connection. These ideas are hard to test. The zero-point field is subtle. It doesn't react like regular matter. Brain activity is complex and noisy. Measuring tiny field interactions is difficult, especially when quantum effects vanish at large scales. But some experiments have explored similar ideas. Tests in quantum biology look for signs that living systems use quantum coherence, brief states where molecules act in sync. Like in photosynthesis, these systems use quantum effects to pass energy efficiently. Some researchers ask whether the brain might do the same in parts of its network. If so, the brain could use quantum-scale events as part of its normal function. This would give it access to the level where the zero-point field plays a role. The link between brain and field would not need to be constant. It might arise during special states, such as deep focus, dreaming, or meditation, when brain rhythms become more ordered. During those times, the brain might act more like a resonant system, tuned to subtle signals. The idea of a field of consciousness also shows up in other models. Some philosophers and physicists suggest that consciousness might not be produced by the brain at all. Instead, it might be a basic feature of the universe. In this view, the brain is like a receiver. It filters and shapes awareness, but doesn't create it. A zero-point field fits into this view as a possible medium, a place where awareness can express itself. This doesn't mean the field is thinking. It means the field might support the kind of processes that give rise to thinking. Like a stage, it doesn't perform the play, but it makes the play possible. Consciousness might arise when the right patterns form, in the right way, at the right time, shaped by biology, but not limited to it. None of this proves that the zero-point field is conscious, but it opens a path for thinking about consciousness as something that includes more than just nerve cells and brain scans. If the field connects all things, and if it contains a trace of all activity, then consciousness might be a process that involves the whole structure of reality, not just the parts we can see. You fall asleep. In your dream, you walk through a city. You see streets, buildings, people. You feel the breeze, hear sounds, talk to someone. None of it seems fake. It feels as real as your waking life. But then you wake up. The city, the people, and the conversation vanish. You were the only one there. The dream was made by your mind. The city did not exist outside of your awareness. That's the idea behind dream solipsism. Dream solipsism says you may never wake up. Not in the usual sense, but in the deeper one. You might be dreaming right now, and everything you see, every person, place, object, is part of your private experience. They seem real. They feel solid. They respond in ways that make sense. But that doesn't prove they exist outside of you. It only proves that they exist in your awareness. Think back to dreams you've had. In them, people speak with you. They act surprised, angry, kind. They have full expressions and complex behavior. You assume they have minds of their own, but they don't. They are patterns in your mind. You create them as you dream. You also forget that you are dreaming. In the moment, you accept everything as real. This matters because it shows how easily the mind can build a convincing world. If it can do that while asleep, why not while awake? The idea behind dream solipsism is that the distinction between waking and dreaming may not be as strong as it feels. Both involve experience. Both involve awareness. You trust waking life more because it's stable and shared. But that trust rests on assumptions, not direct proof. You might say that waking life is different because you can test it. You can touch things, talk to others, make choices. But you do all that in dreams too. You walk, speak, act, and feel. You have memories and goals. You think, this must be real. Then you wake up and realize it wasn't. That shows how the mind can produce full experiences without any outside world. Now imagine that this moment, right now, is part of a dream. Everything you see, the screen, the room, the sky, exists in your field of awareness. You assume it comes from the outside. But what if it doesn't? What if it's more like a dream than you want to admit? The idea isn't that the world is false or meaningless. It's that its form and content depend entirely on your experience of it. This connects with the philosophical view of solipsism, which says only your mind is certain to exist. Everything else might be part of your experience, but you can't confirm it exists on its own. Dream solipsism goes a step further. It says the entire world may be a dream your mind is having, not a dream in the sleep sense, but in the sense that all of it arises within awareness and may not come from any external source. Consider what happens in a lucid dream. You become aware that you are dreaming, but the dream keeps going. You can shape it, test it, and explore it. Yet you know it's still a dream. You might walk through a door and find a city. You might speak with someone who gives you clear advice. Those experiences are detailed and structured, but they are still part of your mind. Dream solipsism says waking life might be a lucid dream without the lucidity. You are having an experience, but you have not yet realized it's not grounded in an external world. This idea challenges what we mean by reality. If reality is what we experience, then a dream counts as real during the time it happens. You respond to it. You feel joy or fear. You act. That makes it part of your life, even if it fades later. Dream solipsism suggests that your entire life might be like that, experienced fully, but not based on anything outside your mind. People often resist this idea. They say, but I don't control what happens. I don't choose what people say or do. But that also happens in dreams. You don't always control the events.
Dream characters surprise you. Situations unfold without your plan. The dream continues as if it has a life of its own, but it doesn't. It only seems that way. Dream solipsism uses this point to suggest that lack of control doesn't prove the world is external. It only shows that your awareness includes things you don't direct. Think about memory. In dreams, you remember things that never happened. You believe you have a past. You think, I've always lived here, or I need to get to work. These thoughts feel familiar and natural. But when you wake up, you realize they were false. Your mind created a fake history. In dream solipsism, that may be happening now. Your memories might not reflect anything beyond this present awareness. They may be part of the story, built into the dream to make it feel stable. You also assume other people have minds like yours. You hear them speak, watch them act, and feel they must have thoughts. But in dreams, people do the same. They act with full detail, but they don't exist beyond your experience. In dream solipsism, the same may be true of everyone you meet. They seem real, but they exist only in the dream you are having. This idea doesn't mean the world is fake. It means that the world, as you know it, depends on your experience. There may be no difference between dreaming and waking except in degree. Both involve awareness. Both involve perception. Both follow patterns. The only thing missing is certainty about where it all comes from. You might ask how to tell if you are dreaming, but dream solipsism says you can't. Any test you run would still be part of the experience. You might say, if I drop this cup, it should fall. It does, but in dreams, objects also follow rules. They behave in ways that feel normal until they don't. Even when something strange happens, you often explain it away. You say, that was odd, but you stay in the dream. In this view, there is no outside point to stand on. You are always within experience. You can question it, explore it, analyze it, but you never get outside it to check if it reflects something else. That's the root of dream solipsism. You live in a stream of awareness. Everything else, time, space, people, objects, is part of that stream. Whether it reflects a real world, you may never know. You may never even wake up. You wake up one morning and decide to wear a black shirt, but you stop for a second and think, what if you had chosen the red one instead? It feels like a small decision, one that could have gone either way. Now imagine that somewhere, in another version of reality, you did pick the red shirt. You walked out your door, had a slightly different day, and met different people. This idea is at the center of the multiverse theory. The multiverse theory suggests that our universe may not be the only one. There could be many universes. Each universe may have its own version of events, laws, and outcomes. These other universes might look a lot like ours. They might also be very different. Some might follow different laws of physics. Some might not support life at all. Some may contain versions of you who made different choices. The theory does not say we can travel between these universes. It says they exist in a larger framework that includes ours. One reason this idea comes up is because of quantum mechanics. In quantum theory, particles can exist in more than one state at once. A particle might spin up and down at the same time until it's measured. Once observed, it picks one state, but before that, it stays in a mix of possibilities. This idea is strange, but experiments support it. One way to explain this is to say that when the particle picks a state, the universe splits. In one universe, it spins up. In another, it spins down. This view is called the many worlds interpretation. If this is correct, then every time a choice is made, a new universe forms. These choices include everything from the spin of a particle to a person deciding what to eat. Each branch leads to a new path. Most of these branches are small and make little difference, but over time, they create vast differences. A person might live or die based on a single decision. In one branch, they cross the street. In another, they wait. There are other versions of the multiverse theory. One comes from inflation theory in cosmology. It says that space expands rapidly in the early universe. This expansion happens in pockets. Each pocket stops inflating at a different time, forming a bubble universe. These bubbles do not interact. They are far apart, each with its own conditions. Our universe is one bubble among many. This version doesn't depend on quantum decisions. It comes from how space-time behaves under certain conditions. A third version comes from string theory. This theory tries to describe all particles and forces as tiny vibrating strings. The math behind it allows many ways to arrange space and energy. Each arrangement leads to a different kind of universe. Some may have different numbers of dimensions. Some may have different constants, like the strength of gravity. If all of these forms are possible, then maybe they all exist somewhere. One way to understand the multiverse is through an analogy. Imagine a library with an infinite number of books. Each book tells a different story. Some are similar, some are strange, some are unreadable, but they all exist on the shelves. You live in one story. You read it page by page. The other stories are there, but you don't see them. The multiverse is like that library. You live in one universe, but others exist alongside it. This view can help explain why the universe seems fine-tuned for life. The laws of physics must be just right for stars to form, atoms to hold together, and life to evolve. Small changes in the strength of gravity or the charge of the electron could make life impossible. That seems unlikely by chance, but if there are many universes, each with different settings, then it's not surprising that one of them allows life. We live in that one because it's the only one where observers like us can exist. Still, many people find the multiverse theory hard to accept. One reason is that we can't observe the other universes directly. We see only what happens here. That makes some scientists doubt whether the multiverse is a scientific idea or just speculation. Others argue that the theory follows from well-tested parts of physics. If quantum mechanics or inflation leads to multiple universes, we may need to accept them, even if we can't see them. The multiverse also raises questions about identity and choice. If every possible version of you exists somewhere, what does that mean for your decisions? Do they matter if other versions of you make the opposite choice? Some say this view makes life feel less meaningful. Others say it makes each path worth exploring. You are here in this branch. Your experience is real. The others do not cancel it out. In some versions of the multiverse, the laws of physics never change. The same particles and forces appear, but events unfold in different ways. In others, the laws themselves vary. Some universes might have no matter, only energy. Some might expand forever. Others might collapse quickly. Some may be chaotic. A few may be structured like ours. You might wonder whether these other universes are real if you can't reach them. That depends on what real means. If a theory predicts something and that theory explains what we observe, then the unobservable parts may be considered real by extension. That's how we treat atoms and black holes. We don't see them directly, but we trust the models that predict them. The multiverse could be part of such a model. You also might ask whether these other universes affect ours. Most versions of the theory say no. The branches do not interact. They follow separate paths. They do not share matter or energy. But some theories suggest that small effects might cross over. If that's true, we might one day find evidence. Until then, the idea remains a way to understand what kind of reality we live in. In the end, the multiverse theory challenges how we think about reality, chance, and identity. It does not offer simple answers, but it provides a wide view, one where what we know might be a small part of a much larger system. Whether or not the other universes exist, the theory invites us to ask how far reality might extend beyond the edge of what we can see. You walk outside and look up at the night sky. Stars blink above you. Somewhere around one of those stars, a planet may hold life. That idea is not new. People have wondered for centuries if we are alone. One theory, called panspermia, says that life did not begin on Earth. Instead, it came from space. It may have arrived on a rock, carried through space by chance. The theory suggests that life is not a rare event, but a process that spreads from one place to another. Now imagine adding one more part to this idea. What if life did not just carry cells or molecules? What if it also carried consciousness? Not in the way we think of human thoughts, but in a simpler, more basic form. A kind of awareness built into life from the beginning. This version of panspermia does not only ask where life came from, it also asks where the first spark of awareness came from. It treats consciousness as something that may travel with life, or even as something that guides its path. Start with what panspermia says. Life may form in one place, like a planet or a moon, and then spread through space. This might happen when a comet or asteroid hits a planet with life. The impact throws rock and dirt into space. Some of that debris may carry microbes. If the microbes survive the trip, they may land on another world. Over time, if conditions are right, they may grow again. This could explain how life began on Earth. It did not start here. It arrived. This idea becomes stronger when we see how tough some microbes are. Scientists have found bacteria that can survive in space. They can handle freezing, drying, radiation, and vacuum. Some can live inside rocks for millions of years. If these tiny forms of life can travel across space, then life might not need to start from scratch every time. Instead, it seeds new worlds like a dandelion spreads its seeds on a wind. Now consider what happens when life starts on a planet. It grows, changes, and becomes more complex. At some point, it begins to sense. Even single-celled life responds to light, heat, or chemicals. That is not thought, but it is a kind of awareness. Later, as life evolves, nervous systems form. Creatures begin to feel, react, and choose. In humans and other animals, this leads to what we call consciousness. In standard science, consciousness is seen as a product of the brain. It arises when matter becomes complex. But another view says that consciousness may not depend on matter. It may not emerge from it. Instead, it may be part of the base layer of reality. In this view, even the simplest forms of life carry a spark of awareness, not full thought or emotion, but a basic sense of being. If this view is right, then panspermia with consciousness becomes possible. When life travels through space, it brings more and cells. It brings a seed of awareness. This awareness may not guide life in the way we guide our actions. It may not make choices, but it may be part of what keeps life going. It may shape how life forms grow and adapt. Awareness, in this case, is not added later. It is built in. One way to picture this is to think of water in a sponge. The sponge takes many forms. It may be small, large, dry, or wet, but the water remains part of it. Life may be the sponge. Consciousness is the water. The form changes, but the presence stays. If life spreads through space, then this presence may spread with it. Some thinkers have linked this idea to quantum theory. In that field, observation seems to play a role in shaping outcomes. Some believe that even simple forms of awareness might play a part in how matter behaves. If that's true, then consciousness may not be something that just watches the world. It may be something that helps form it. In this case, the spread of life is also the spread of awareness. This may also explain why life seems so ready to grow. When we look at life on Earth, we see it everywhere, deep under ice, in dry deserts, inside rocks, and around boiling vents. Life adapts to harsh places. It finds ways to grow in cracks, in air, in soil. It seems to want to live. This drive may not be random. It may come from the link between life and awareness, consciousness, even in a simple form. You walk outside and look up at the night sky. Stars blink above you. Somewhere around one of those stars, a planet may hold life. That idea is not new.
People have wondered for centuries if we are alone. One theory, called panspermia, says that life did not begin on Earth. Instead, it came from space. It may have arrived on a rock, carried through space by chance. The theory suggests that life is not a rare event, but a process that spreads from one place to another. Now imagine adding one more part to this idea. What if life did not just carry cells or molecules? What if it also carried consciousness? Not in the way we think of human thoughts, but in a simpler, more basic form. A kind of awareness built into life from the beginning. This version of panspermia does not only ask where life came from, it also asks where the first spark of awareness came from. It treats consciousness as something that may travel with life, or even as something that guides its path. Start with what panspermia says. Life may form in one place, like a planet or a moon, and then spread through space. This might happen when a comet or asteroid hits a planet with life. The impact throws rock and dirt into space. Some of that debris may carry